Yes, please start whenever you're ready.
Hi, yeah, I think we can then start. So hello to everyone. So my name is Jukka Talvitie. I'm currently a university lecturer at Tampere University, and my background is in communication systems, mobile networks, and so on, and especially in signal processing methods used in the communications. But last years, maybe 5 to 10 years, I've been focusing a lot to positioning domain, and also using the position information to communication, so-called location awareness. And today we will discuss about the positioning in the 5G domain. And before going forward, so just like to provide thanks to, especially to Mike Koivisto and the rest of the positioning group in the Tampere University, who's been participating all the results and stuff that I will discuss today. But yeah, overall, this today's lecture, I have a quite huge number of slides, maybe 45 or so. So most of the slides are kind of a good to know material, and are some including, for example, tables. If you're further interested, you can check those and the references therein. But I just wanted to include it there so that you can find it from the data that you will be, all the slides that you will be shared. But anyway, something that is often forgot when moving to the 5G topic and the positioning is often the requirements, especially regarding the positioning. So people are just talking about the accuracies in most of the time, although there are lots of other aspects to consider also. So I will start with those. Then I will highlight a few positioning approaches, the potential ones for the 5G, why certain approaches are better than the other. And then I will discuss some of the kind of challenging scenarios. And by this, I mean that many of the positioning studies and many kind of fundamental research related to this topic are often considering very ideal environment. And in the 5G, the target is to work basically everywhere and in very critical, mission critical systems, and we need to ensure that the functionality is available everywhere. So what can we do in those kind of situations? And then in the last one, this part I will go through relatively fast. It's not related to the positioning in the positioning point of view, but it's related on how to use the position or the location information to improve the communications performance. So the rest of the 5G system, how it can use the position information. But if we go a little bit to the history and the basic concept, what is the positioning in 5G meaning is that, of course, the development on these different generations in mobile networks, it starts already at the time when the new technology is there. So, for example, when the first LTE network started to appear, the discussions on the 5G started, and now the discussions on the 6G are already going nicely forward. So in 2015, there was certain requirements provided, for example, and specified later in 2016 that these certain data rates and availability and number of devices and mobility and all the things that are related to the 5G communications performance. But one of those was also positioning, which is now new compared to the earlier generations like 4G and 3G. So the positioning was already in the beginning, it was considered as part of the whole 5G development. So if we go a little bit forward in 2016, there was this, well, it was already probably presented a little bit earlier, the fundamental idea, but this famous 5G triangle. So we can divide the 5G use cases into three main categories, like this extreme mobile broadband, which is kind of providing very high data rates to mission critical systems to provide high reliability and low latencies. And then the kind of IoT, the massive machine communications part, where the number of devices kind of explodes to huge numbers. And now in this triangle, we cannot see the positioning. So where it is now. Well, the answer is simple. It's basically everywhere. So the positioning is actually, or at least it can be considered as part of any one of these. As we see that for the mobile broadband, the high data rates, if we're able to use positioning for mobility management to kind of help the users in case they're switching the base stations or so, or in the ultra reliability scenarios to kind of be proactive and to be prepared in situations that are going to happen based on the positioning data and tracking IoT devices, monitoring sensor networks, all these kind of things. They all can be related to positioning, so it's there, and as we live in the world, at least fundamentally live in the world that considers 4 dimensions: the X, Y, Z, and the time. And these positioning solutions are exactly focusing on those. The time is also a very important part of that, as it is, for example, in the satellite-based positioning system. So that's why it is basically included everywhere. And if it's not yet used, it will probably use in the future for different verticals that the 5G is considering. And 5G has probably been discussed already during this event, that it's going to basically serve everyone and everybody, as it's going to be very flexible. The number of verticals is huge, the use cases where the 5G communications can be used, but it's also then a matter of questions. Okay, we used to have like Bluetooth, Wi-Fi's, mobile networks to kind of fulfill certain communications needs. They all have a very important role in the ecosystem. But now 5G tries to be somehow be everything, and that is only possible when we have a flexibility in the system. And flexibility starts already from the very physical layer, how we're able to transmit the actual radio waveforms and what kind of parameters we can use there, and also in the higher layers then. So meaning that certain parameters which are making the difference are now flexible, and this is also specified to be part of the 5G positioning services. So the positioning should work also in that level, not providing like a sub-meter accuracy in all the time everywhere, but there are certain use cases. If the battery usage is the main thing, then we have a less accurate positioning, but long battery duration, and if we are working in some very mission critical systems, we need to be very reliable and accurate and have a low latencies, and then the battery consumption is higher, for example, as an example. So this kind of flexibility has to be there, and it's been originally designed in the 5G from the beginning and in the 5G positioning. So what is needed? So this is a very naive example. I don't actually like it, but I still want to include it here as it is kind of raising the main question. So if we have a positioning accuracy of less than 10 centimeters to say, is it enough? Well, of course, it's enough for many cases, but of course, if we look at the big picture, if that was only for one specific environment or scenario, if we were just lucky with that, of course, it's not enough. So we need to fulfill all the requirements, and also how long it took, for example, to take this kind of an accuracy. At least mathematically, if we're able to take an infinite number of measurements, we're kind of in many, without any bias, we're kind of converging to maximum accuracy or minimum accuracy. So the positioning accuracy is only small part of the whole figure. Maybe the major thing is in the positioning accuracy, but there are many other key performance indicators specified in the 5G. So this is one of the main messages that I want to convey during this talk, is that if you're in the future or so considering these kind of positioning things in 5G or 6G or 4G, doesn't matter, also pay a lot of attention to what is actually needed in order to get certain kind of positioning accuracy. What is the cost of that? Because typically these things these different key performance indicators cannot be maximized jointly, but they are kind of an interdependent. So positioning accuracy obviously is important, but then in a mobile scenarios, the speed of the target or the heading of the target is important. Timing is very important in certain. For example, nowadays one of the one of the very important use cases for the satellite-based positioning is actually acquire time. So for example, in stock markets and so on, the timing accuracy is important, the availability, so in which part of the network in percentage you are able to receive certain kind of service, the latencies, meaning that when you request a position, when you actually are able to use it, when you get it, also the latency for the first time that you utilize the network, that can be much higher than the overall latency. That kind of regular latency, how often you are able to update your position, how much power you use it, and how many numbers of devices you can support in your positioning systems. All of these are extremely important. And depending on the use case, if you think about the triangle that we talked earlier, there was, for example, mission critical stuff, which is related to latency and reliability and so on. But there was also IoT, which means that, for example, certain sensors need to survive like 10 years without changing the battery and still get the positioning information. So they are interdependent targets. And the continuity, reliability, integrity is extremely important. So for example, can you trust in your positioning result or not? And if you cannot, how fast you can actually alert the system that something is wrong. This is extremely important in, for example, in transportation systems, like if you need to, for example, train management, railway management systems, if something goes wrong, how fast is the alert coming? The authentication and security, meaning that are you really working with the trusted sources to acquire your positioning information, and is your positioning information secure, the privacy issue, and so on. So these are it's a huge set of requirements, but it's important to say that sometimes if you're, let's say, if you're doing some industry related scenario where you have a robot moving there and you need high reliability, low latency, high accuracy, and so on, in order to have the industrial process ongoing and working all the time. But then if you're just looking for a nearest restaurant when you're moving at the city center, you wish not to use the battery, and you don't really care if it's 10 meters away, the correct position that you get. So that's just as a very simple example. So always pay attention to that also. The accuracy is only part of the whole picture. And then also where the positioning service is obtained. So there's 3 different kind of areas of positioning for positioning services in 5G. So this first one, so-called 5G positioning service area, is the actual area where the 5G is available, as is the basic 5G service. So the area of the coverage of the 5G network. So that is for use cases that must work in any 5G environment. But then, as I mentioned already, for example, some mission critical systems, then you can have specified areas in the network where you, for example, introduce an additional infrastructure to get better performance. So again, when somebody says that you're able to receive sub-meter accuracy, it's probably not for the whole 5G network, but it might be for a certain use case that requires that. So again, very important thing to consider and remember throughout. Okay, this is one of the slides that there is lots of details in these tables, but if you want to take a look from the shared material, you can do that. There is also the reference to the specifications. But the main message in this slide is that there is at the moment the 7 different service levels for the positioning performance specified by the 3GPP in the 5G specification. So this is for release 18, but it's been there already from at least release 17, this same table basically. So depending on your requirements, you're able to get accuracies from service level 1, which means about 10 meters in horizontal accuracy. By the way, these are 95% time you can receive this accuracy. So it's not the mean accuracy. The mean accuracy will be even higher. But like from 10 meters to a few tens of centimeters, depending on the service level. And also then the availability and the latencies are the important parameters there. Already the vertical accuracy, because many of the use cases are related to actual 3D space, for example, UAVs, like drones and so on. They are one of the use cases for the future, very important ones. And then one thing more before going to the technical stuff is that do we really need the 5G positioning service? This is one of the questions that I've heard quite many times, and it's a valid question, of course. We have nowadays very good and accurate positioning systems already, like satellite-based navigation, for example. So again, if we rely on the specifications and the studies given there, if our accuracy requirement is less than 50 meters, in this table you see different colors. On the right-hand side column, you see this used positioning technology. So in each row, you have one positioning technology, 3GPP LTE, which means 4G networks. Then there is this terrestrial beacon systems, which means similar to satellite-based positioning, but on ground. So you have these beacon locations which are dedicated for positioning purposes. Then there's Wi-Fi, Bluetooth-based positioning, and then satellite-based systems with the regular ones that you can find in your cell phones, the GNSS in general, and then high accuracy, so dedicated GNSS receivers which can have a higher accuracy. So if we are only targeting at 50 meters, we see lots of green color, which you can see from the upper part of the slide, is that the green means that you are able to meet the targets, and then the color fades towards the red one, which means that you never basically meet the targets. But now we see lots of green in the table. So 50 meters is quite nicely covered already by the current systems. But still, by the way, notice that the current systems don't necessarily serve the key performance indicators that you're looking for. So for example, battery consumption, if you use some sports tracker type of application, if you go jogging and measure your distance, typically your cell phone battery is going down relatively fast because GNSS is eating energy quite a lot. But then 3 meters, now we start to see lots of red, and only what is on the green is basically the satellite-based systems. And also there in the indoor, we don't have any more coverage. And if we go to the high accuracy systems and talk about tens of centimeters, then only the kind of an open areas with the satellites, high accuracy satellite systems can meet the targets. And there is clear need for a positioning service. And these tables were only for the accuracy. And of course, the other indicators are also important. For example, the reliability. So then to the actual kind of more technical oriented thing. So how to perform positioning in 5G? So first of all, what are the signals what we can measure in the 5G? So too often people refer to only these positioning reference signals, which are nowadays specified to the downlink. But there are also many other kind of signals of opportunity available. So we can use also other reference signals, and it can be done both in the uplink and downlink. In downlink, it means that the base station is basically transmitting the signal, and it's measured by the mobile device, and the uplink is vice versa. And in both directions, we can have very good positioning signals, which are able to use the full bandwidth and therefore reaching very nice accuracies. So lots of reference signals. Also, it means that if we are using the reference signals that are already there as a kind of a working together with this kind of an underlying communications network, we don't even introduce any new overhead because of the positioning. So it's the positioning becomes as a side product of the normal operation, which is of course quite nice. So we can of course do the positioning there. If we're able to measure at both ends, at the mobile device and base station, we can do the positioning in downlink and uplink, or either one or both. We can consider different methods separately or together, and these different methods include, for example, time of arrival, time difference of arrival, angle of arrival, angle of a departure, and these kind of methods. As this lecture is more on the kind of a general level, we don't go into details, but it's good to discuss a couple of things because they're related to the actual motivation of using the 5G in these systems. So why 5G is great for positioning, or then 5G and beyond, so 6G and so on, why they are great. One thing is that we're moving towards higher carrier frequency, so meaning that the system operates in the higher area of frequency. So we have a little bit smaller wavelengths, but because of that, there is much more bandwidth available, and the bandwidth makes this kind of time resolution very good, and it means that we have very accurate ranging. Also, the high carrier means high path loss, so it means that the signal is attenuated quite a lot. That means that we will have a denser network. So there are more base stations per area than in the previous generations. That means that we have probably better visibility to these base stations. And also the kind of a proximity of the base stations in general also is kind of indicating high accuracy. And then higher carrier frequencies also predict higher antenna arrays. Use of larger antenna arrays means that we are able to have these kind of highly directive transmissions, and if we have a directive transmissions, we are able to estimate the angles also, and the more directive is the transmission, the better angle estimation we are able to achieve. So these are the kind of key ingredients in 5G, why it's so good and appealing for positioning. There are 3 slides about these basic positioning techniques. I will just go through if some of the audience is not familiar with these basic positioning techniques. But one of the main ones is the time of arrival or time of arrival based methods, where we basically assume that we know the time of the transmitted signal time and the received signal time. So we're able to measure the delay of the propagation. And since we know that the signal propagation speed is basically light speed, we are able to estimate the distance from between the transmitter and receiver. And then if we have multiple measurements of these, we are able to use this kind of trilateration principle as seen in the lower right figure. To position the device. But there's of course one question mark here, which is the synchronization. So in order to do this, we need to really have a synchronized devices at both ends. So this is in practice very significant challenge. If we want to remove or at least mitigate the effect of this clock synchronization needs, we are able to use time difference of arrival methods, where we do the exactly same kind of a measurement of the time of arrival, but then we actually, in the positioning phase, we don't consider those separately, but we consider differences of those. And that by that processing, we are able to remove the clock offset between these user devices and the networks. But even in this case, the network is assumed to be perfectly synchronized. So the base stations, for example, in the figure on the right are having exactly the same time. But now the UE time doesn't anymore make a difference. This is beneficial from the clock point of view, but now instead of 3 measurements, we basically have 2 measurements. From the 3 base stations, we can have only two independent measurements. So the accuracy is not so good with the time of arrival method. And then the angle-based methods is the last one that we briefly show here. So in the angle-based methods, they are backed up by the fact that if we are able to have directional antennas, for example, antenna arrays that are able to do beamforming, we are able to estimate the target angle. Here we don't need clock synchronization in any way, and that's of course a huge thing from the practical things point of view. But again, there is one thing that we need is we need to use the antenna orientation. We need to know that in which direction is the antenna pointing, because all the angles are always estimated with respect to the antenna itself. So the antenna's kind of a orientation is one issue here, and then another one is that unlike with the timing-based approach, the angle-based approach are if we talk about positioning error, if we have let's say 1 degree accuracy of the angle and we are 1 meter away from the base station, we can have very good accuracy. But then when we go to the 1 kilometer away from the base station, this angle kind of spreads in position domain, meaning that we have a very poor positioning accuracy in those scenarios. So therefore, angle estimates, they are having these kind of certain areas where it can be used in an efficient way. As an example of a positioning approach, we need to first consider in the studies that how can we even have an example or do the evaluation for positioning systems if we don't have the 5G networks. Nowadays they have started to emerge, so they are starting to be there, but the coverage is still, of course, poor, and we want to study the kind of eventual positioning thing. We need to rely on simulations. And if we rely on simulations, we need the simulations to be somehow valid and as realistic as possible. Luckily, there has been specifications on how these things has to be done, again, by 3GPP. And one of the approaches, probably the most complicated one, but most realistic one, is also this ray tracing based thing. So we kind of have a 3D map of the environment, and we simulate the radio propagation through the 3D map and get the kind of a realistic idea how the channel looks in different locations in the map. This Madrid map was actually specified already in these METIS channel models in 2015. It includes kind of an open areas and these kind of housing blocks and different street widths. So it's kind of a nice tool for evaluating the positioning accuracies, and it's also, as it including the specifications, different organizations can use the same thing and compare the results between. And one thing more to decide, important one from the practical point of view, is that what is the positioning approach? Are we going to measure the signals at the base stations or at the user devices? Well, one thing, if we want to use this kind of vertical thinking in the 5G, it would be beneficial to have the positioning information updated at the network side. So by that way, doing the positioning based on the uplink signal, so the signals transmitted by the UEs, it makes the positioning data to be instantly available at the network. So the network knows, for example, the locations of different UEs and can therefore work to manage the, for example, some kind of transportation systems or so. And also then all the heavy computational load is at the network side, meaning that the batteries of the devices can be the load for the battery can be reduced. Then if this is the case, we have the scenario where the user device sends the signal, and the signal is received by the most likely very close by base stations. The base stations, based on the received signal, they're able to receive and estimate the time of arrival, so the distance to the UE and the direction of the UE, so the angle estimation. And then the base stations will fuse these measurements, these angle and timing measurements at the network in some kind of a fusion center. And then from the fusion of these measurements, we are able to receive the position estimates and also for example, the clock errors between the user devices at the base stations if we want. So next, there is actually a demo video about the positioning in this Madrid map. So in this demo video, on the left-hand side figure, on the bigger figure, you see the red crosses, red cross, which is the true user position, and then the purple and blue crosses, which are estimated positions. The purple means using only angle information, and the blue means using ranging and angle information. And the used bandwidth for the signal is 100 megahertz here. But as we do the positioning, we're also doing synchronization of the network. So on the right-hand figure, you see the overall picture where the user is moving there, and you can see these kind of timing offsets of different base stations given in microseconds there. And when the user moves in the area of the base station, it can actually help the network to synchronize itself, and therefore this network gets additional information, additional data from the positioning. And the synchronization, of course, it can be beneficial to many other things happening in the network. So again, on the left, you see these ellipses, which are showing the 95% confidence areas for the positioning information. The other one is for the angle, and the other one is for the timing plus the angle. And as you see on the right-hand figure, when the red cross approaches the new base station, their synchronization error drops into kind of a nanosecond level. And that's it. But then, what if we have not an ideal case, like in the well, it wasn't an ideal case. It was ray tracing based simulation and so on, but there was at least line of sight available all the time. But if we don't have, or if we have orientations moving at the user devices or even at the base station devices, can we do the positioning in those scenarios? Well, the thing is that we can. Now, for example, we can have a situation where a building is blocking our line of sight signal. So notice that now we are not able to measure anymore the true distance between the UE and the base station, because all the paths go actually another route, which is a longer one. So the geometry doesn't hold anymore for the positioning. So what we have to do is actually, we need to actually estimate all the unknown parameters, which are in this case also the points where the signal is reflecting or diffracting or scattering in the environment. So in this figure, you see that there is a base station on another side from the building, and the UE can have whatever orientation, and when it sends the signal, its signal is blocked by the building, but of course the reflected signal then the reflected signals can reach the base station in this case. However, the positioning becomes much more difficult. So we cannot use any more the traditional methods. If we have the unknown orientation and if we have the unknown this reflection locations, the number of variables increases. But now, as a side again benefit of the positioning systems, we are starting to also estimate the environment, not only the position of the user device, but also the environment. So that means that we are doing mapping, an imaging type of a technology where when we move in the environment, we are able to start to build a 3D map about the environment. But as I said in the beginning, we can do these kind of things. We are not limited into scenarios with an ideal conditions like line of sight or known orientations or clock offsets or so. But the thing is that then things get much more difficult. For example, the computational complexity of mapping these different objects in the environment can be 1,000 or 10,000 times more complicated from the computational point of view than doing regular positioning in a line of sight scenarios. So these kind of things, of course, there are many methods, but just to give you a an idea. In this figure, what you see is we use this kind of a sampling-based method and particle filter-based method to estimate these environments. So on the left, the figure on the left, you see this circle, which is the base station, and then on the right, you see this UE location, the square one, and then these diamond shapes are actually the non-line of sight paths, the reflected paths, and you don't have anymore the line of sight directly there. But based on the more complicated algorithms, we are able to track both get the distribution for the user position, the probability distribution or likelihood for that, and also for the scatter and this reflection location. So if we would move in this scenario, we would actually start to draw walls and these objects in the map. The question is how accurate we can get with these. Well, again, let's not focus on the curves or the detailed results, but let's just focus on the sentence below, is that we're able to show that even without a line of sight and even without known device orientation, we are able to actually estimate the user position with the sub-meter accuracy, and also to estimate the orientation of the device with sub-degree accuracy. So there are lots of potential there, but as I said, it requires much more computational power in order to reach this thing. Then one more question to consider is that, okay, how to use this location information. I think this starts to be more and more important in the future. This positioning starts to be, I mentioned already, this simultaneous localization and mapping, but we start to talk about also sensing and kind of having radars in devices and base stations to learn from the environment, to sense things in a passive way from the environment. Basically working as kind of as a radar principle, so that we get reflections from objects, and then we are able to estimate their locations and kind of do this imaging of the environment. But those can be used for several verticals in the industry in commercial way. But then one question is how we can actually use the positioning information to improve the actual 5G communications performance, so the performance of the 5G system. Well, the traditional approach is to do measurements, take measurements all the time. So especially when you're actively having a connected communications with the base station, you're doing channel measurements, and based on those, the base station gives you resources in which frequency and time you can send and receive signals and data. Well, if you do measurements and you report the measurements, it's kind of a reactive approach. It means that we are kind of already late when we kind of get the information at the base station. But of course, if the measurement interval is high enough, in certain cases, it's of course enough. But the positioning is more predictable. As an example, if you have a car and you have a speed of 100 kilometers per hour in a highway, you can say that the car is not stopping in 1 millisecond or so. We have a physical limitations for the movement, but also kind of a behavioral based kind of patterns in the movement that we can consider there. But the main message is that depending on the kind of a time scale that we use the positioning information, we are able to do kind of proactive decisions. So we can kind of avoid bad situations already before they kind of start to occur. I have a couple of examples of those, but before showing those, there are just a couple of examples how this positioning is actually tied to the location information. Again, I'm not going into details, but if you're familiar with certain kind of basic principles in the electromagnetic wave propagation, you're probably finding here some of the key points. But here in these figures, you see the X is a kind of a position. It can be vector of X, Y, Z coordinates, for example, and XS is the position of the base station. Well, the position is of course related to the X, the user position is related to the path loss. So how much the signal attenuates, that's clear. It's related to the propagation delay. So depending on the distance between the positions, you get the delay and therefore the distance. The Doppler, the derivative of the position, gives you the velocity. The shadowing means that if you're in certain location getting bad reception for your cell phone, if you move half a meter, you don't necessarily get a better reception. There's a spatial correlation there that is related to the position or the difference between the position. In the multiple antenna systems, there is angle relationship between the positions. So the angle is defined based on the positions between the transmitter and receiver. In routing scenarios, in order to find the minimal number of hops in mesh networks or IoT networks, it's a matter of position. The interference, how severe is interference between two devices or multiple devices, is a matter of positioning difference. And also the proactive allocation of resources, so the positioning can help you in it's a predictable behavior as discussed before. So as the location is such an essential element there, so of course it should be used to enhance the system performance. There is lots of research on this area, and I'm not going into those in this talk, but as an example of a couple of very kind of understandable and easy kind of obvious ways is given here. So first of all, if you're in an urban environment, for example, a vehicle situation, you're coming into cross section, you've been served by a certain access node, but soon you are turning left or right, so the upper figure in this slide, and you will go kind of a non-line of sight situation to the current base station zone. So based on in which direction you're going to turn, you're able to start pre-allocating your resources so to get prepared in the next base station. So the kind of a mobility management guidance through positioning and prediction of the position. Also in the lower figure you see there's a kind of football stadium here. It's kind of a topical because we have the European Championships going on. So the content prefetching. So if there is in the stadium, if there's a match ongoing, there is basically the capacity is full for the base station serving the stadium. So if you're driving a car and go on side of the stadium, and then you're watching a video, you can kind of prefetch all the data to the video as far as you reach for the access node number 5 in the figure, and you can continue downloading. But you will be kind of again doing proactive things in order to improve the system. I included this slide here just to give an idea how well we are able to predict the vehicle positioning in time, but I'm not going into this detail. There is a reference in the paper, but just to say and indicate that there is also research on how well this kind of a prediction of vehicles or anything can be done in a realistic environment. But as a last note, I want to emphasize the fact that the location information, too often researchers and people studying this topic consider the location information just from the kind of a estimate point of view, so that it's a kind of a mean of the distribution, meaning that we have only the position estimate. But always the position, we don't know it for sure, it's an estimate. So there is always some uncertainty in the estimate. The uncertainty can be, of course, very small or very, very large. And if we take this uncertainty into account, we are able to go deeper in how this positioning really can affect the system. As an example here, we have a so-called location-based beam forming or beam steering. So, as I said, in the 5G and beyond systems, the beam kind of beam forming becomes an essential thing. It means that we're able to direct our energy in a certain direction and therefore have higher capacity, better signal-to-noise ratios in the target. But now, if we use narrow beams and if we use the position estimate to target to kind of choose the direction, the thing is that with narrow beams, if the positioning uncertainty is too large, we kind of miss the target. So with narrow beams, we achieve very high beam gain, but we can easily miss the target. But with the wide beams, again, we can hit the target most likely, but then we have a lower beam gain. So we have actually some kind of a compromise. What should we choose based on the uncertainty of the whole thing? Traditionally nowadays, this beam, the direction is chosen based on the measurements. So we just do kind of a beam sweeping or beam training and then decide based on the training that what are we going to choose. But it turns out that the system capacity interestingly, it's a function of positioning error level. So this figure, it's a little bit complicated, but on different colors of curves, you see different beams, and these beams have different beam widths. So the dark red color is the narrow beam with 2 degree beam width, and the yellow is the one that has a very wide beam. And this dashed black line is that we don't use beam forming at all. And we are able to see on the x-axis where the positioning error is shown, the kind of a standard deviation of that when the positioning error is high, so on the left side of the figure, the capacity of the system is maximized with the wider beams. And when the positioning error is the deviation, the uncertainty is very small. So we have a small error deviation, like 0.25 on the right-hand side of the figure. We are able to use these narrow beams and to receive a very high capacity of the system compared to the lower. But we need to know the uncertainty, of course. And as an example, what this means is that if you try to use a flashlight, for example, to hit a mosquito, for example, you're able to get with the regular flashlight, you're able to get the mosquito there very easily because the kind of light beam width is very large. But if you try to hit with the pen laser or something, it gets much more difficult. But with the pen laser, you could get a higher capacity, but you cannot use it because you need to have very good positioning accuracy. And this understanding that the uncertainty is one of the most key things is important here. But yeah, I think that was all for today. So I gave a kind of an example of some of the consideration of the 5G positioning systems and what is required there and how to perform there, what are the opportunities, and also how to use the positioning information in the system itself. But yeah, I think, by the way, there is in the material you find this link. There is lots of videos and other stuff included there if you're interested to see more on this positioning domain. But otherwise, I think I'm kind of ready for the lecture now. What is the time? Do we need to, or is there some time for the questions or? At least in the chat there is what is the relationship between noise and high frequencies. Basically, the thermal noise with the frequency is still used in the system. It's not changing from the noise density point of view, but in the higher frequencies, basically there is larger bandwidths used, so the amount of noise is increased because of the larger bandwidths. But yeah, then when we go to the extreme frequencies, then also the kind of noise type is changing. Thermal noise is not anymore kind of white. But with the current frequencies, that's still the case. So it's only a matter of bandwidths, basically. Yeah, about the satellite system. Actually, the satellite systems are considered part of the 5G positioning. So the 5G positioning doesn't really it doesn't limit to the system where we have only like 5G signals based positioning, but it can use whatever positioning means. Satellites are one of the things, and there is this assisted GNSS already also considered in 5G as in the 4G. So satellites will be part of the system. And indoors is of course something that the satellites cannot do. If we have only one kind of a radio head or something, if we are able to get the or in such cases with few radio heads, is there any methods proven to implement positioning? So yeah, of course everything can be done. So with the single, it's only a matter of number of unknowns and number of measurements you're taking. So if you have only one remote radio head, then you need to have at least timing and ranging in order to get the position, and then depending on the accuracy of those, you're able to get certain positioning accuracy. But yeah, of course, you need to still pay attention to the coverage and so on. But yeah, with one base station, that's actually one of the directions in the future that is now a hot topic, that we will consider only one base station for localization at the time, because then we don't have so much issues with the synchronization between the base stations. And as I said, even with one base station, it's possible to estimate also these non-line of sight scenarios, so that fits to indoor scenarios quite nice. So the target can be behind the corner basically, but it becomes much more complicated. Could beams with less signal strength be used to determine positions? So the beams, well, depending, there are many types of beamforming methods, so-called analog and digital beamforming, and depending on how many samples from the array are you able to get at once. But for the positioning signals, we typically don't need the same signal quality as for the communication signals. So the positioning signals can be detected much further away. So if the communication system uses beams that can give you, for example, 20 decibels gain, the positioning could be actually working with the 0 dB gain, because we don't need to decode all the data. What we need is just the time of arrival or the angle information there. So it's a little bit different, but yeah, there is lots of options there. And this beam sweeping can be used for angle estimation also. So if we compare beam powers, then we are from different directions, we are able to estimate the angles by just comparing the powers of different beams. Are we running out of time, or what is I don't know about the time scale, or is there time for the questions? I'm happy to answer, of course.
There is still some time for questions.
Okay.
Thank you for the extremely good lecture. At 2 p.m. Tiia Ojanperä from VTT will start her lecture, and until then there is some time for questions, so please feel free to take as much as you have time for.
Yeah, sure. Yeah, I have the chat open, so if we want to ask through chat or then through audio, both is fine. Yeah, in general, we live kind of at times that there is so many different options, so many different kind of approaches how to do things, and we clearly are in a situation where things starts to merge. So we used to have like separately positioning, separately communications. Then we started to introduce this sensing and radar-based things also on the RF, these kind of regular communication systems, and these mapping things. And now everything started to be integrating, and we see lots of research which has this kind of integrated solutions. So using the radio signals in such a way that we get every single information out from there that we can use for something. So it's a huge topic at the moment. And personally, for example, I've been now working with all of those that I just mentioned. So sensing and so radar and sensing based applications, so localization and mapping based things and so on. And also one thing that I didn't mention here is of course machine learning, which is also raising its head in this area as one of the methods to solve these things. Okay, regarding high-speed vehicles, what could be more efficient in positioning, NTN or broadband? What is the NTN here? What does it mean? Okay, so well, at the moment, these mobile, at least the 5G, the velocities, the defined accuracies are up to 500 kilometers per hour. We are able to do updates probably in close to 10 millisecond intervals, even faster if needed, but I think that's the key thing here. So with high-speed vehicles, typically the thing is that it's easy to predict. I've been studying, for example, high-speed trains and the train management system. So to get kind of warning aspects there if something goes wrong with the train and if it stops stopping or going different tracks or so. But at least there, based on some of the customers that we've been working with and so on, we've been hearing always the comment that satellite-based navigation is not sufficient to meet the requirements there. So we will probably need both. So I think always when we start to talk about reliability and these kind of things, there is no 5G, there is no 6G or so that can alone do the task, but it's a combination of both. What's the biggest challenge in Europe regarding management systems using 5G? So yeah, different management systems. So if you talk about the 5G itself, or then some other management like transportation management system or so on, I think it's probably first of all sharing the information. So there is always the position is kind of a, yeah, for example, transportation. So sharing the information is one of the challenges. So it's a practical challenge, not the kind of a challenge of technology. So depends on how the manufacturers or the customers or so are willing to share their vehicle information, although it would be done in a kind of a private way and so on, and not basically we don't need the kind of a information of who's driving or whose vehicle it is, but in many cases it's enough to say that there is a vehicle there and it's approaching that direction and so on. So the positioning thing is that the privacy thing is one thing, that's one practical challenge, and there is lots of discussion in the society also regarding that. So that's one thing. But then I think, where is the updated information, where it is located? So these kind of, especially in transportation systems where we consider high mobilities and so on, there is challenge of moving the information in the system, and if some base station knows where you are, does the next one where you're going to enter know where you are, and there is often also this kind of tracking algorithms involved. So you have some kind of a prior information on the location, and then you do measurements and update your information. So to share these priors and different measurements between different base stations, I think that's one of the challenges there. I think from the technology point of view, we start to be there. So if we get the bandwidths and so on, and also dense network or enough dense networks and good coverage, I think that's not going to be the issue. I think it's about these ecosystem-wise issues. So how the manufacturers and so on are willing to contribute to these kind of things where you share, for example, position information between vehicles. That has been there for the vehicle manufacturers for a long time. Every single manufacturer seems to trust on different kind of a vehicle-to-vehicle type of a communication scheme. Although it's been studied for a long time, there is still no unified approach between the different vehicle manufacturers, for example. So those are, I think it's on that kind of a level maybe. But I think the technology is there already now.
Yes, thank you very much. I think that 2 minutes until the start of lecture from Tiia Ojanperä, so let's wrap it up at this point. Then if there's some more questions, please contact Jukka Talvitie directly or via the course organizers will be sending the questions to you via email if some occur. Yeah, but thank you very much for the great lecture.
Yeah, thank you.
we can start already whenever you're ready.
Okay, good. Thanks. So good afternoon, everybody. My name is Tiia Ojanperä. I work as a research team leader at VTT Technical Research Center of Finland. And also I'm the Finnish country coordinator in the Celtic Next 5G Safe Plus project. My today's talk will be focusing on 5G and how it can be utilized for enabling cooperative, connected and automated mobility. And I'm focusing today especially on the case of improving road safety in this context. So first, some background to the topic. So as we all know, effectively operating and safe road network is really a critical requirement for any modern society. And for instance, the EU has a vision to reach close to zero casualties in traffic by the year 2050. And the current technological transformation that is taking place in the automotive industry at the moment towards more and more connected and increasingly automated vehicles can really help in improving road safety and optimize road maintenance, and this way help us achieving these ambitious goals. So far, there has been a lack of sufficient communication media as well as scalable data processing solutions, which have hindered the wide-scale adoption of this kind of a more advanced vehicular services. And now 5G is expected to bring a solution to this. Here is a probably quite familiar triangle of the 5 different 5G features and capabilities, and a little bit overview how it can be utilized for enabling cooperative, connected and automated driving. So the automotive applications, they in fact can be utilizing all the different features of 5G. So for instance, the enhanced mobile broadband capabilities required for instance, for video transmission that is needed for a remote control in cases where there is a teleoperation. For instance, if automated vehicle has run into some difficult situation, so the control center will be needing a real-time video feed from the vehicle and then sending commands back to the vehicle. Then real-time digital map exchange is another quite bandwidth consuming example. So the vehicles are needing very accurate map information to increase their situational awareness. Then coming to the more safety critical and also latency critical applications. So for instance, exchange of maneuver coordination information between vehicles is requiring then the ultra reliable and low latency communications from 5G. And then finally, for instance, smart city environments and of course the roads in general, they can be then in the future integrating many different kinds of sensors that can be then utilized, for instance, for traffic management and driving support. And quite typical and familiar applications are, for instance, parking availability information for vehicles. Then when we are talking about automated driving, so there are different levels for this, depending on what is the driver's and the vehicle's role in operating the vehicle. So ranging from level 0, where the driver is self-handedly responsible of controlling the vehicle, all the way to the level 5 full automation, where the system can cope with all situations automatically and the driver is no longer required. And in today's systems, we are many times quite often talking about the level 3 automation, where the system has control over or the vehicle has control over the specific use case, and then driver only needs to be available in case they have to take control. And here we can consider either human drivers in the vehicle itself, or then teleoperated driving, so that the automated vehicle can be taken over remotely if needed. Then automated driving is also requiring different kinds of support from the infrastructure. And here we are coming into also to the need of connectivity between the vehicles and the infrastructure. So here also we can recognize different levels for the infrastructure support, ranging from the conventional infrastructure where the vehicle in the lowest level has to manage by its own sensors and recognize road geometry and road signs by itself. Then the second lowest level is that the vehicle is receiving digital map information in the static format, and this way is able to enhance its knowledge of the surroundings. Then when there is a digital infrastructure available, so the vehicles are able to get dynamic digital information, so more detailed warnings of the surroundings, weather information, incidents, etc. And then the two highest levels, so there is the cooperative perception and then cooperative driving, where on the highest level, the vehicle movements can be guided by the infrastructure, or groups of vehicles can be guided in order to optimize the overall traffic flow. Then with 5G in specific in mind, so 3GPP has defined some generic use case categories that were identifying features that can be especially benefiting from 5G, for instance, from the low latency point of view. So there are five different main categories where most of the 5G V2X use cases are falling into. First of all, advanced driving, where the vehicles are able to exchange trajectories or maneuvers related information and this way coordinate their operation. Then extended sensors use case category, where the vehicles are then exchanging either raw or processed sensor data between themselves to increase the situational awareness. Then remote driving, we discussed already a little bit. So the control center then taking over the vehicle in cases where needed. And for this, there is a need to have this real-time video sharing and then control data back to the vehicle. Then the vehicle's platooning case, so where the vehicles are traveling in close distances and the front vehicle is somehow controlling the whole platoon movement. So for this kind of a scenario, 5G will be enabling smaller in-vehicle distances and providing benefits such as less fuel consumption for the platooning. And then finally, 3GPP is also identifying general aspects where 5G can be benefiting all V2X scenarios where there are some interworking or communication related requirements that cannot be met with LTE-based solutions, for instance. Then here is a table, for example, key performance indicators for selected V2X use cases. In order to give some kind of an idea that what kind of end-to-end latencies we are talking about for some of the services or data rates, and of course the vehicle speed is one factor affecting also these previous criteria, that is what is finally the performance required for the vehicle to be able to react to the situation. And also many of these services are requiring quite accurate precision so that they are useful, for instance, for automated vehicles. So the first example, emergency brake warning, there is only the tight latency KPI. The messages themselves are very small, so no specific data rate requirement identified, and the velocities considered for the vehicles are in the order of 180 kilometers per hour. Then the last three examples are then more in data intensive examples. So sensor sharing, either processed sensor data or raw sensor data transmitted between vehicles, and in order to have this kind of a collaborative perception over the environment. So very tight latency requirements also here when traveling on high speeds. Then the see-through application where, for instance, if vehicles are traveling in a queue, so we can send the front view of the first vehicle to the vehicles traveling behind, and this way the other vehicles will have better idea what is happening in front of the first vehicle, perhaps a truck or bus, and then adjust their driving or decision making accordingly. And then teleoperated driving. So here there is the need for video transmission to the control center, but the velocities in the vehicle side are lower in this case when the vehicles are guided to some safer location if they are facing some problem. Maybe one thing to also point out here that many of these or all of these examples regarding the data rate, so these are all data transmitted to the uplink direction from the vehicles, and this is also when considering the very large scale adoption of the services. This may be one challenge even for 5G if we are finally sending all the data from all the vehicles to the network. So talking about V2X, so what are the technologies, communication technologies, what we are actually considering here? So in this V2X context, we are looking into both short range and long range communication, and then different technologies can be used for both. Traditionally, the short range communication, so vehicle to vehicle and vehicle to infrastructure, has been based on the 802.11p wireless LAN standard, which has been then standardized in Europe under the ITSG5 label. And this technology has been deployed already in some degree, but the same technology that is considered in the US, for instance, under DSRC, this has recently faced challenges as the FCC reallocated the frequency of DSRC to other uses late last year. But anyway, in Europe, ITSG5 is still considered, and this kind of a hybrid approach is prevailing. So giving support for both this ITSG5 and then the new cellular-based solutions, so that there is a choice among these technologies. Then coming to the cellular, so 4G and 5G based solutions. So in the short range, we are using the PC5 interface for the vehicle to vehicle and vehicle to infrastructure communications, and then for the long range, there is the UU interface. So the PC5 basically means that the data transfer and communication is not going into the core network, but so that we can then guarantee lower latencies in this case. And then if you look at the picture, so also for the roadside infrastructure, today there are also other technologies considered. So for different kinds of IoT applications, so NB-IoT or LTE-M are also for many smart city applications, for instance, considered technologies. So anyway, quite heterogeneous and multiple technologies considered in this context, in addition to 5G. Then besides 5G, so the multi-access edge computing will be also another important enabler for many of these vehicular applications. So with the MEC, we will be able to, first of all, shorten the transmission path and this way decrease the latency. So this is done by bringing the applications and services and data processing physically closer to the vehicles, and so that we don't have to anymore send all the sensor data, for instance, to a remote application server. And also privacy is one thing that we are considering that MEC will be benefiting also, so that the data collected from the vehicles is staying in the local area, and only processed warnings and information is sent outside. So this is also more lucrative in the privacy perspectives. So potential applications that are utilizing and benefiting from the edge computing. So sensor processing, of course, so that we don't have to send all the data all the way to the remote cloud, for instance, and to have this very real-time situational awareness and shared situational awareness applications among multiple vehicles in the area, and to allow also latency critical applications like the maneuver support. There are, however, some open issues still remaining before this can become a reality. So of course, this intermec communication is something to be still solved, and of course this kind of a multi-operator architectures, because depending on the vehicle manufacturer, one might be using one operator services, another one other operator services. So how we can efficiently share information between the services in this case. And 5G end-to-end slicing, of course, is another interesting factor for the automotive applications. So instead of needing to have a separate infrastructure for the automotive services, with the network slicing capability, there is the possibility to run multiple logical networks as virtually independent business operators on a shared physical network infrastructure, which of course will be more cost efficient, for instance, for the services. And with this slicing capability, it will be possible to customize the network capabilities for the different automotive use cases. So different data speeds, latency, reliability, security, as needed, can be supported and guaranteed for these use cases. And since, of course, again here, since vehicles are moving between countries and potentially between operators, etc. So this kind of a global slicing feature will be important to ensure service continuity also in this kind of situations. With that generic introduction of the 5G benefits for connected and automated mobility services, next I have some ideas about the current development activities and trialing that we have been doing around these topics at VTT. So here is an overview of our 5G CCAM project portfolio. We have 3 EU projects and 1 Celtic Next project running at the moment, focusing on these issues. All of them have a little bit different focus and, of course, different consortiums. For instance, the 5G MOBIX is looking into the 5G cross-border trials and focusing on the release 14 and 15 deployment of 5G services. And VTT's use case in this project has been to study the cooperative collision avoidance for automated vehicles. Then 5G Drive is actually a collaboration project between EU and China. And here we have been looking at intersection scenarios with traffic lights and also intersection safety cases. And the third EU project, 5G Routes, is then focusing on the later 5G releases, 16 and 17, and also in the cross-border context, and this time looking into the Baltic corridor ranging from Finland, Estonia, and Latvia. And here we have been looking into see-through for automated overtaking and then sensor sharing use cases. And the fourth project is something that I will tell you today a bit more about. So going to the next slide with more details on the 5G Safe Plus project. So as said, this is a Celtic Next project, so international collaboration project. And we are aiming to make innovations on 5G-based vehicular connectivity, distributed data collection and processing, cybersecurity, and novel road weather and safety services that can be benefiting connected and automated vehicles, road operators, road users, and other third-party organizations. We have 17 industrial and academic partners in the project from 5 different countries. So in addition to Finland, we have Romania, Canada, Luxembourg, and Turkey participating in the project. And Sitowise here in Finland is the project coordinator. It's a 3-year project, so we are now first year in the project, so doing the specifications, and then next couple of years we will be doing more of the trialing and experimentation on the different solutions. The approach that we are taking in the 5G Safe Plus project is that we are studying 4 5G-inspired automotive use cases that we have selected on the basis of that they are foreseen to benefit the society by improving road safety. And here is an overview figure of the overall scenario or solution and the context that we are looking into in the project. So some key elements being intelligent connectivity and data transmission solutions for the vehicles and the infrastructure. And here we are looking into 5G, but also other V2X communication technologies. Then distributed data processing is one important enabler. So we are considering approaches or the most optimal approaches for processing data. So of course something can be processed in the vehicles themselves, then something in the roadside units, in the MEC, and then finally in the cloud. And then on top of this connectivity and data processing infrastructure, we are then developing also novel road safety services that are then relying on the actual sensor data and information that is collected from the vehicles, as well as other sources. So we are also considering, for instance, weather stations that are installed alongside of the road as a source of information for the services. And then, of course, cybersecurity is a critical requirement for this kind of a connectivity and services delivered to the vehicles. So this is considered also in the project. Then going into the actual use cases that what we are looking into. So we have 4 different use cases. The first use case is focusing on the road weather, road safety, and road maintenance services. And it has a little bit broad context, so it has been actually split into 2 sub-use cases, looking into the later testing and piloting. So the first sub-use case is titled Safe Driving in All Weather. And here we are aiming to share road weather information between the road weather stations and connected vehicles. And this way provide drivers or driving assistance functionalities better information of the prevailing weather, and so that they can then adapt the driving accordingly. Then efficient winter maintenance is the other sub-use case. So of course here in Finland and also in our partner countries like Canada, there can be very harsh winter conditions that are making driving and also road maintenance difficult. So this kind of a digital services can really help in optimizing winter maintenance operations and also provide cost savings to the road operators. So we are looking into salting of the roads or optimizing the maintenance of, for instance, bus stops, so cleaning them from the snow, etc. And the focus is more on the low-level roads, so less traveled roads, where really benefits can be foreseen with this. If we are collecting data from vehicles which are already traveling on the roads, and this way avoid having the road operator personnel actually to drive through the road network. The use case 2 is then looking into the specifically on the hybrid connectivity and its usage in the context of this kind of a road safety services. And the idea here is that, of course, for instance, 5G coverage and all the 5G features most likely are not available everywhere where the vehicles may be traveling. So there will be situations where the vehicles will have to resort to other means of communication. So the idea is to allow the vehicles to dynamically choose and use the best available communication methods, including 4G and 5G, the short-range communication methods, and also satellite connections in some very remote or rural areas. And this is needed for the additional reliability and coverage for the services. And here we are also considering different types of services to be delivered to the vehicles, like obstacle detected, vehicle situational data, HD map updates, etc. And adaptation of the services to the network capabilities is another interesting topic, as of course the technologies have different performance, and maybe not all services can be supported by all of these technologies that are available. Then the third use case is then focusing on automated driving and especially on road safety information. Actually, I have more details on this later on, so maybe we can skip it for now. Anyway, it's focusing on safety critical information and detection of pedestrians and objects on the road. And then use case 4 is looking into these services for cyber attacks information for the vehicles. So the aim is to be able to detect and block cyber attacks for connected and automated vehicles and smart transportation systems. And the way that we are looking into this also quite broad issue. So analyzing events and sensor data for anomalous behaviors is one approach that we are looking into the project. So here is the overview of the 5G Safe Plus physical architecture that is actually showing the different types of communication media that is used by the vehicles to communicate among each other, as well as between the vulnerable road users, for instance, as well as towards the distributed cloud environment, including the RSU edge, the MEC servers, and then the cloud services. So for short range, for instance, we are looking into the 5G PC5 capabilities, in addition to the traditional ITSG5 features, depending on the vehicle capabilities, or for instance the roadside capabilities. So which communication technologies are supported by the weather stations, for instance. Then satellite connectivity is also supported by some of the vehicles in these scenarios that we are looking into. Yeah, and then the communication towards the mobile networks through the UU interface, and then the vulnerable road users may be carrying their cell phones and other equipment that are also connecting to this overall architecture. So here is a little bit more detailed view on the use case tree, analyzed in terms of a sequence diagram to see what is actually happening there. And this is something that we are now developing and implementing, looking into the pilots. So in this scenario, the idea is that there is a roadside camera that is then producing data processed in the RSU edge to detect the pedestrian walking on the road in a place maybe where the pedestrian is not supposed to be. Then there is this collective perception message warning sent using the MEC server to the vehicles in the area. So there is a connected and automated vehicle that is approaching the pedestrian, and then there is a connected motorcycle that is also receiving the warning about this pedestrian. And then in this scenario where there is also potential for dangerous overtaking, so we are also looking into the usage of the new maneuver coordination message being standardized by ETSI to allow the automated vehicle and then the motorcycle to negotiate on the order of overtaking, so that there are no hazardous situations coming up in this kind of a case. And another aspect that we have been studying is this vehicular data management framework. So of course, efficient communication of this vehicular data and warnings is really a requirement in order to implement this kind of a new services for the automotive use cases. And in this context, we have been considering a layered information broker framework for the collection and distribution of vehicular data. And the idea here is that all of these different entities or different layers are having a local information broker that is managing the data collection and data dissemination in its own. And the actual data transfer is then based on the publish subscribe architecture, and it can be implemented with different kinds of protocols. So far we have been considering, for instance, DDS, MQTT, AMQP, or COPE for communicating the information. And this kind of a layered approach, of course, allows tailoring the implementation and the used protocols to the needs of each entity. So inside the vehicle, we have been using, for instance, DDS protocol for the signaling, and then from the vehicle towards the MEC server, MQTT, for instance, and AMQP is considered as this kind of a more federated approach towards between MEC servers or cloud servers for the communications. And yeah, the benefits of this layered approach is, of course, that we can then support this new kinds of architectures where we have MEC servers or roadside edge servers, etc., so that we can then efficiently communicate the data in the overall architecture. And as said, so first year into the project, so we have been doing a lot of the specification type of work so far, and we are now implementing the different components. So our aim is to then validate and pilot at least part of these use case features in the coming couple of years. And the approach that we are taking here is that we are aiming to utilize 5G test networks and vehicle test tracks that we have available in the participating countries. So, for instance, here is a picture of the SOT 5G winter vehicle test track that is run by our partner FMI in Sodankylä, so Finnish Lapland, where we can have this kind of a very wintry conditions for the testing. Then in Tampere area, we have more urban environment for testing with, for instance, with the automated vehicles.
Good
and
morning.
then a little bit more
Good
small
afternoon,
scale
and
testing and laboratory testing. We are then also utilizing VTT's 5G test networks that we have in the city of Oulu and Espoo. And also considering technologies that are not yet commercially available. So we are also using simulators to evaluate their performance. For instance, for the satellite connectivity, we can then be modeling new satellite constellations and evaluating the communication performance towards the vehicles in that way. Here is an overview of the VTT's 5G test network. I'm not going to go into the details, so just the idea that this network is available both in Oulu and Espoo, and this is also connecting to the Sodankylä test network. So VTT is operating that one in collaboration with FMI. We have features for 4G and 5G available, and also satellite capabilities to test also those features in real pilots. And also, of course, some of the features like network slicing is something that is currently work in progress. So it's not yet fully supported by the test network, but let's see if still during this project that we have. And then VTT is also having different kinds of research vehicles that we are utilizing in the project for piloting. So we have an automated vehicle called Martti, and it's been equipped with different kinds of sensors, including LiDARs, radars, stereo cameras, etc., and also different types of connectivity support. So also UU and PC5 interfaces. Then this connected motorcycle is something new that we have been developing in this 5G Safe Plus project. So we are also devising the motorcycle with, for instance, with radars and then connectivity capabilities. And then for some of the roadside data processing testing, so we have this mobile roadside unit also available that can be carrying, for instance, this kind of a roadside cameras for our third use case for the pedestrian detection, and also it has different connectivity capabilities. I still have a couple of demo videos. Maybe there is still time to take a look at them. So these were just first videos developed during this first year of the project, just to kind of bring to life these visions towards the use cases and the pilots. And the first video is showcasing the first capabilities that we have been developing for the connected motorcycle and its interactions with the automated vehicle. So hopefully this will be playing Well, so this first scenario is demonstrating the collision avoidance utilizing the LTE and 5G connectivity between the motorcycle and the automated vehicle. And there is a user interface that we have been developing for the motorcycle to warn the driver or the rider of the dangerous situation. And then the second case is showcasing the left turning in an intersection where we are using the mobile roadside unit for warning the vehicles. And then to the second demo video, which is then showcasing the integrated satellite and terrestrial connectivity for autonomous vehicles and the related simulations that we have been working on. So the vehicle here is driving in a rural area, and it has some sensors on board and different communication options for data transfer. And the vehicle is detecting an obstacle on the road. And then sends a warning through the terrestrial network if it's available. And if the terrestrial network is not available, then the message is transmitted via a satellite. And we are also studying the future LEO mega constellations that will be enabling connectivity and this kind of a service provisioning to vehicles worldwide. Okay, some quick conclusions before ending the presentation. So 5G and edge computing, they will be key enablers for this kind of a novel connected vehicle applications that can be used for improving road safety. And they will be enabling scalable and reliable communication and processing of the vehicle sensor and camera data in real time. And this way, allowing localized and more intelligent services. And in the 5G Safe Plus project, we are currently preparing for trials that will be taking place in the coming 2 years. And our aim is to show the benefits of the 5G service concepts in terms of improving road safety. So I thank you very much for your attention. And here is my contact information in case you have any questions or comments, and also further information about the 5G Safe Plus project can be found from the project website. And also here are the links to the demo videos, so they're also available in YouTube. Thank you.
Thank you very much, Tiia Ojanperä. And next up in 15 minutes, Muriel Medard will come and hold the next lecture. If you have any questions for Tiia and Tiia, you still stay on the line, you can ask them. And you still have time for a few minutes.
Yeah, maybe a couple of minutes. Yes.
And if there's no questions, then
Next up, Professor Muriel Medard will take over the stage. She is Cecil H. and Ida Green Professor in the Electrical Engineering and Computer Science Department at MIT. Welcome, Muriel.
Noise, which may seem counterintuitive, but we'll see is a very powerful as well as optimal scheme. So, what is the current need when we think of 5G, since 5G is indeed the topic of our discussion today? We talk a lot about ultra-reliable, low-latency communications, and what that means is you need enough rate, but it's not just rate that you need, you particularly need timeliness. On the other hand, it seems like these two aspects of ultra-reliable low latency are really, given the current approaches used actually in 5G, are actually running against each other. The ultra reliability is usually achieved by adding coding at the physical layer, and coding not only adds redundancy, but in traditional codes such as low density paracheck codes, it also adds a huge amount of length. We'll see that more afterwards. On the other hand, low latency, you would like to have basically as little redundancy, as short a length as possible. So inside this simple notion of ultra reliable low latency communications, there seem to be two aspects which are almost like an oxymoron, or at least are at odds with each other. So how have we been managing it? Well, the way we've been managing it is really by adding more spectrum. If you look at the recent spectrum auctions for 5G, for instance, in the US, you're looking at almost $100 billion of spectrum. And the idea is we're doing things inefficiently, but we're just doing them faster, so that by doing things faster and efficiently, you actually, or at least getting the low delay that goes with the low latency requirement. Okay, so what we're going to be looking at today is how to change the approach of coding at the physical layer. Now, when we're talking about changing code, we're actually not going to look at changing the coding, because anything that requires you to change the code is almost doomed. It has to go through 3GPP. It has to go through basically what's a very closed environment in order to have any sort of innovation. What we can do, however, is to decode any code, whether it be existing codes or new codes, we'll see, as long as you have low latency, which is what we want. Okay. We have these principles of coding that I just want to go very quickly over. This is sort of setting the stage for what do we mean by coding. There's sort of two different aspects to coding, which we usually think of as being completely separate, but we'll see that they're actually intimately linked. One is what we call source coding. So source coding means that I have data here, for instance, the gray data, and I do compression or source coding to get rid of redundancy in the data in order to have a more efficient representation. So maybe imagine that each of these blocks is, say, 100 bits. There's a lot of redundancy in the data. I can do source coding, say gzip, and turn those 400 bits into maybe 200 bits. Okay, then when I have this data that's compressed, I want to send it over a channel. Now what I'm going to do is now I'm going to add redundancy, which may seem a little funny. First I take out redundancy, then I put in redundancy. I'm going to add redundancy, but the reason for adding the redundancy at the channel coding is because once it's going through a channel, there may be some effects that are going to affect the data. And so some of the data is going to be affected in the channel by some deleterious effects. And the redundancy is going to allow me to reconstruct the original data, which can then be source decoded to have the original representation. So just in terms of very light notation, let's think of this, often we call it the source, that's denoted by S, so that's the original data. We're going to do some excuse me, compression or source coding, which is going to shrink the source according to the entropy. H is the usual notation for entropy. So H of S is the entropy rate of the source. In the example that I gave you, the entropy rate was 1/2. That means that I can take the data and shrink it by 50%. Then I'm going to do a channel code. And what the channel code is this addition of redundancy. And it's usually characterized by a rate R. The rate R shows how much redundancy I have. So for instance, the rate that I'm showing you here is 2/3, okay? Because I have 200 bits of actual data for 300 bits of transmitted bits. And I'm going to generally denote by X the coded data that's transmitting over the channel. Now, I told you that the channel has a deleterious effect. Usually the way we're going to show that deleterious effect is through some additive noise N. So for instance, think of having a bit flipped. When a bit flips from a 0, 1 or 1 to 0, what we're doing is we're actually adding a 1 modulo 2. So we're XORing with noise of 1. If nothing's happening, then we're XORing with a noise of 0. So this additive model is actually pretty powerful and is sort of a canonical tool of communication. So that's the noise N that happens in the channel transmission. Okay, what are we doing when we have the source or the source coding? Really what we're saying is, even though there were 2 to the 400 possibilities, because there were 400 bits to start out with nominally, in effect, because of the redundancy, there's actually a much sparser set of possibilities that I need to worry about. With probability almost 1, almost all the possibilities are really just can be described with 200 bits, which means that instead of really having the full 2 to the 400 possibilities, in essence, I only have 2 to the 200 possibilities, okay? So here, for instance, I told you H was 1/2, say N was 400. So I went from 2 to 400 possibilities to 2 to the 200 possibilities. You know, of those 2 to the 400 possibilities, were the vast majority of them were basically not anything I should worry about, you know, almost never happen. When I'm going here and adding redundancy, what I'm doing is I said, of the data, I have these 2 to the 200 possibilities. And what's going to happen is I'm going to turn it into these code books, and these code books are of higher length. So you would think, okay, in this code word, if I have 300 bits, do I have 2 to the 300 possibilities? Well, no, I don't, because they came from these originally 200. Okay, so I have, even though I have 300 bits, I really only have 2 to the 200 possibilities. So here N is now 300, R is 2/3, so I still have 2 to the 200 possibilities, which corresponds to my original data. Now, what happens when I'm sending it? When I'm sending the X, what happens when I'm sending X through my noisy channel? Well, I have this noise, which is coming to be added. And if the noise was, say, that every bit was hit so that, you know, with probably 1/2 it got flipped or not, you know, I could actually not get anything through. The noise would basically completely kill my ability to reconstruct the data at the channel output Y. So what we have is a noise which has some sparsity. So in the same way that there was sparsity in the original data, there's sparsity in the noise. Actually, there's a lot of sparsity in the noise. The noise is generally very, very sparse. We'll see later how sparse that is, which means that you really have a very small number of bits that, on average, that's flipped. If I were to think of this as being able to compress the noise, it means that this entropy of the noise would be very small. And if I were able to just look at the noise and describe it as strings, then I would really only need 2 to the NHN strings. I would only need NHN bits in order to describe the noise, if I were able to describe the noise. So let's think, what would be the nicest noise that could ever happen to me, given that the noise has to happen and given that it has to have this entropy HN? Well, if you will, the most well-behaved, polite, unobtrusive noise would be a noise that sort of just, obligingly places itself at the end of my transmission, right? So if I could send the data and say, well, I'm going to send the data, I realize I need to have, there's going to be some noise. I'm just going to leave a little space at the end, NHN bits, so that the noise can just place itself in there. Surely that's the best thing that I could do. Then I'd be able to separate the data that was transmitted from the noise that was added, if the noise was just sort of segregated to the end of the transmission. So clearly, that's the minimum thing that I can do. And in that case, what I would have is my channel output would have n bits. It would be 2 to the n possibilities for my channel output, which would correspond to the 2 to the nr possibilities of my data and the 2 to the nhn possibilities of my noise. Okay, so in order to be able to figure out, or another way to think about it is for me to be able to figure out from Y what X was, it has that I'm also able to figure out the noise, because if I figured out X and I subtract X from Y, I get the noise, okay? So basically what's happening is we say, if I look at my channel output, it needs to be that N, okay, is at least as large as NHN plus NR, if we look at the exponents, which basically means that R has to be no greater than 1 minus H of N. And this, for a binary system, we've been discussing everything in binary so far, this actually is capacity, okay? So this is the easiest proof of capacity you will ever see. You don't need to take a one-term course in information theory, though you're welcome to do it. I teach them. This is the easiest proof of capacity you'll ever see. Okay, so given this notion of what it means to be able to send, that this is the upper bound on rate, this is the biggest that R can be, and still be able to get through in a way where X with high probability allows me to recover the original data. Can I achieve? Can I actually go ahead and achieve this this rate? And the idea here is that you can, but the approach that has been taken so far is to say, I understand the math that I just presented to you at a high level. Of course, there's a lot more detail in the literature. There's a huge literature on the topics I just mentioned. Can I take that math and try to translate it into engineering? And what that has meant is that N has been very big generally. So we're looking at a very large N. And also that R, even though we talk about capacity, remember that R could be up to 1 minus H of N. What does that mean? It means the channel capacity, given that the bit flip probabilities, I told you I would get to this, in typical settings such as in 5G are like, 10 to the minus 3, 0.1%. Which means that the capacity would be roughly 0.99, something very, very large. Actually, because we use these very long codes and they're really difficult to decode, I'll tell you later about it, because people don't, it's hard to do. The rates that are sent are generally massively, massively lower than the capacity. Okay, so we're talking with rates as low as 0.2, and almost never do you actually get up to 0.91. The other aspect is that there's always been decoders that are code specific. So, you cannot use, say, a Berlekamp Massey decoder with an LDPC. That doesn't work. And also you have a huge amount of delay, which is added to make the channel appear like you have independent, identically distributed errors. So you have interleaving over thousands of bits to make the channel appear ID. Okay, so it's basically the approach that has been taken up until now. What we're proposing here with GRAND, guessing random additive noise decoding, is instead to focus on this engineering need. We want high rates. I want low redundancy. I don't want to add a whole lot of bits here. Remember here I was adding, a lot of bits. It's a rate 2/3 code, whereas normally I should be, so I'm adding, 50%, whereas I should be able to add 1 or 2% from the theory. I want to be adding those low redundancies. I want to have flexibility. I don't want to have that every time a new code comes out, 3GPP has to have a huge soul searching and years of work because, you need to put a new code, you need to put a new piece of hardware for the decoding. We don't want to have to do that. We want to permit innovation and have new codes come on as people develop them for whatever needs of development. And I want to have low latency. I want to control code length. I don't want to have to go to long code lengths if I don't have to, just because, there's some math from the 40s that tells me I should. And I should also try to avoid interleaving, spreading out the code, the bits over multiple code words if I don't have to. So what we're going to be able to do with this guessing random additive noise is make the math look like the engineering. Okay, so how do we do this? So remember that I had my Y, which has the output, and it was the X plus N. I'm denoting here plus with a circle. Think of this in terms, say, if you're thinking binary, in terms of bits. So I'm adding noise where 0 is no effect from the noise on that bit, and 1 is flipping the noise on X, okay? And we've already discussed the fact that there's 2 to the NR of these XNs. So even though they're length N, because they came from a smaller data string, there's only 2 to the NR of them. And there's 2 to the NH of these noises, okay? And the standard decoder, what it does is it looks at the Y and it goes through all the X's in effect and says, given the Y that I see, and given that I've created the X with some sort of structure, what is the X that most looks like this Y? Okay. And basically that's really what all decoders right now do. And so you can see why the encoders and the decoders are matched. The decoder really needs to be deeply aware of what the encoding structure was up until now. We're going to get rid of all that. What GRAND does is instead is going to identify the noise by looking at, identify the transmission X by looking at the structure of the noise. And what I mean by structure, it really means sparsity. It doesn't mean that the noise is structure. It just means that there's a probabilistic structure, not necessarily a deterministic structure. And so what I have here is I have inputs, which are the Y, okay? And I'm going to put out the best estimate of the code word, and a Q here, which is a measure of the reliability, in effect, of how good my estimate is. What do? I'm going to guess the most likely noise effect. If, for instance, I have a channel, which is, say, a very standard channel called the binary symmetric channel, where a 0 goes to a 1 or 1 goes to a 0 with a probability of about 10 to the minus 3 that I mentioned before, then that's my most likely noise effects. It's actually that nothing happened. Most of the time, nothing's going to happen. Or, very little is going to happen. Maybe I have a single 1, a single bit flip. I'm going to guess the most likely noise effect. I'm going to subtract the effect. Okay, here you can think in binary, you're subtracting the noise, but really this will be more important later when we looked at self-information, subtracting the noise effect. And if I subtract the noise effect, say by taking out, by XORing with a putative noise sequence the y of n and see what kind of x of n estimate I get. If that's a member of the code books, if that's a valid code word, then I'm done. So how are we using the code book now? I'm using the code book now really just as a hash. All of the issues around code construction, which we'll discuss in a couple of slides, are really completely irrelevant. The code book doesn't have a particularly clever structure that's trying to, fight against the noise and be able to recognize why. All it is just being able to say, yeah, I'm in the code book or not, okay? And the first time that I find that this removal of the noise effect from y is in the code book, I'm going to return C star of n and also tell you how many times it took me, because the more times it took me to guess, the more likely it is that the noise was a little odd, and therefore the less certain my estimate is. Now, this decoder that I just showed you is universal, because all it needs is just being able to verify whether or not something's in the codebook. It's not using the structure of the codebook or not. And that module is separable from the noise effect subtraction, iterative subtraction, one at a time that we're talking about here. So the complexity is a function of the noise. How long does it take for me to guess the noise? Not of the code rate, not of the code structure. Okay. Now, this may seem too good to be true. So we have actually developed a chip which just was accepted to ESS Circ, which is one of the which is the premier European circuits conference. And what we do in here is we have a stream, like I just mentioned. So here are my bits coming in. We put it through some noisy channel, which adds noise, and then we decode. And our chip is able to decode all codes, not just existing codes, such as Bose-Chaudhuri-Hockenheim, BCH codes. It can also decode polar codes, CRC-aided polar codes, which are in the 5G standard. It can use CRCs, which are up until now only used generally for detection, very seldom for correction, and very, very limited cases for correction. We can use the matches error detection codes. We can use random linear codes, which were codes that actually had been offered as possibilities in the 60s and the 70s, but up until now had not been doable. We can use those codes. So we can use, we can make those codes possible. We can also use Reed-Miller codes. So we can actually decode any code. Here's the chip, and here's some block error rates. So this is for a code word. What is the block error rate? These are what we show in this panel B is for existing codes, and what we show in this panel C is for codes for which there existed no hard decoder. A hard decoder is a decoder that makes a decision as to whether 0 or 1 was sent. Other decoders, such as traditional polar codes, need soft information. This one is a much simpler receiver. So you can see here's the theory in dashed lines. The full lines is what we measure. So our decoder is not just theoretically optimum, but actually operates optimally over all of these codes. Over codes that could be done with hard detection, codes that could not be done for hard detection. Polar and CRC-aided polar could be done with soft detection, where you have more information about the receiver than just whether it looked like a 0 at the receiver, or whether a symbol just looked like a 0 or 1. Some of these other codes, such as random linear codes, CRCs, up until now did not have a decoder. So for the first time ever, it's now being decoded. I'd like to also point out, because remember we're talking about ultra reliable low latency, compared with all the other hard decoders, we have the best latency in terms of how much time it takes per code word. Again, remember what we're trying to do is we're trying to do one specific code word as quickly as possible. Please do note that actually we can do every single code. I know we've mentioned it, but it's sufficiently surprising and revolutionary to point it out again, where all these other decoders are specific to particular code. This is not an implementation, but an architecture, a nice architecture that was done by another group in Canada from Professor Gross using our algorithm. So it uses Grand. They're looking more at storage. So we don't have delay numbers for them because it was not implemented, but they have some very nice architecture in terms of parallelization. Now, I mentioned soft information. I showed you that we've done a hard detection decoder. A lot of systems, and particularly in 5G, which is the topic of today, use soft information. What is the soft information? At a high level, it means that you have a signal that's coming off the electromagnetic spectrum, and that you don't only demodulate and decide whether something is 0 or 1, but you also give some extra floating point information about how close to the 0-1 boundary it was. Okay, and one of the systems, for instance, just to look at again 5G that has been implemented in the control channel uses CRC-aided polar code. What are CRC-aided polar codes? It means you have a polar code and you have a list of polar. The polar decoder gives you a list of possible codes, and then use a CRC, cyclic redundancy check, in order to pick from that list which one is an actual code, and that gives you the information. If you look at Grand, Orb Grand, S Grand, what we have here is Grand is the hard detection. Soft Grand, which we presented last year with our Ken and I with our students at Mid-Solomon, uses the full soft information. This is the actual maximum likelihood. Again, just to emphasize how surprising this is, particularly for those of us who spend our lives working in this area, that you can actually now find a universal maximum likelihood decoder, which is something that we never thought we'd be able to do, and it's just based on the fact that the noise is sparse. And there is also an approximation called Orb Grand, ordered reliability bits, that Ken Duffy just presented at ICASP actually last week. I told you before that we don't need to go to these long code block lengths. Really, what we care about is how much redundancy there is. So this gives you an idea, depending on different block lengths, how many bits there are in the code, of the rates that we can do. So if you have a long block length, we operate at high rates. If you have a short block length, we can also operate at low rates. This is fairly surprising, and these are unpublished results, so you're getting a sneak preview. This is using CRCs, which, as I mentioned up until now, have only been used in general for detection of errors. Some very limited approaches for satellites for trying to do some error correction, but it's very, very limited. It's definitely not universal. Here what you see is a CRC-aided polar code, again from the standard. This is using the sort of list decoding that I mentioned before, with a list size of 16. Just to give you an idea, this list size of 16 is actually quite generous. This is something where most chips would use a somewhat small list size. It's also something to bear in mind that the complexity actually goes up. The complexity of decoding usually goes up exponentially with the list size. So this is basically the state of the art, or somewhat better. Okay, this is implementing this algorithm that I mentioned here, but I didn't in my slide, but I didn't point out, which is the approach used by Samsung, licensed from University of California, San Diego. These are polar codes without the CRC. This is if you were using only this decoding, and instead of decoding down to a list, you decode it down to a list of multiple, you decode to a list of just one. Okay. And what we see here is that we do much better than the state-of-the-art decoder. Polo codes without the CRC are just not very good. Sad to say, but certainly here they're not doing very well. This is Polo code only. It's the original Polo decoder. This is using our approximation to multiple likelihood, the ORB, and you can see that we do as well again as the original optimum with this universal decoder. So it's not just universal, it's optimum. But the codes are they're not that good. It's sort of funny. Almost all codes are good. You really have to construct, because remember, we're only using the code as a hash check. So you have to almost go out of your way to make codes that are not good, but almost all codes are good. But this one has a structure that actually doesn't make it very good. If you use a Polo code with CRC 11 or CRC 24, if you use a list decoder with CRC checking, it does make a difference. A smaller CRC actually will do better. If you use ORB Grand, or basic, if you use Grand, it doesn't make any difference. And even if you did that, instead of having some amount of redundancy from Polo codes and some amount of redundancy from the CRC, because again, remember, we don't need to decompose into first decode, then go through a CRC. To us, it's just a code, right? It's just a code. We're just decoding. We're just checking whether it's in there or not. The checking, by the way, I should have mentioned, is very simple, because you're just basically checking whether the syndrome is 0 or not. If you have a CRC-aided Polo code, that is actually a linear code. And so the check is just doing a linear operation. It's quite straightforward. Okay. So what we see is that except for Polo codes, if you do the decoding correctly, if you use Grand, they all do the same. So if you think of all the work that has gone into making all kinds of clever codes, low density parity check codes, Polo codes, Reed-Muller codes, Reed-Solomon codes, mentioned both Chaudhry-Hockenheim codes, et cetera, et cetera, et cetera. They all do the same as just a CRC, which is, if you will, the poor cousin of codes. Is such a simple code. So what happens really is it's not really the code, unless you go out of your way to choose a bad code like the Polo code here. They're all good. They're all good as long as you decode correctly. Same thing here when you have, say, CRC versus a Polo code. Again, the Polo code is not very good. The CRC-aided Polo code is fine. It does well, but it just does the same as the CRC. So I hope I convinced you of this new vision, which is to make the engineering look like the math. Make the math look like the engineering, not the engineering look like the math, which is the way we've been doing it up until now. And the way we've been doing it up until now has led to a proliferation of codes, to huge discussions in 3GPP and in journals and so on. Whereas here it's just saying, look, the code construction is very simple. It's very, very simple. Just decode correctly. Just decode correctly using Grand. With this, I wanted to leave time for questions, so I wanted to have a discussion. Now I have 45 minutes. I left about 10 minutes of discussion. I would like to encourage you if you're interested in Grand, to go to our website for the Grand Decoder, which we host at MIT, and you can see the latest papers, a video overseeing some of this work and other materials. And with that, I'll stop and take questions. if there are no questions, I can go through some more material, but it's up to you. How many people want me to take questions, or how many people would like me to go through some more material? I'm going to do a quick. So you can just give me a sign on the you can just talk to me on the chat if you want. How many people would like
Good afternoon, everyone. Did you know that the low latency that 5G enables plays a crucial part in the development and utilization of real-time communications? For instance, immersive arts and extended realities, extremely low latency is crucial. This would be enabled by 5G technology. Vice Dean of Aalto University School of Arts, Design and Architecture, Rasmus Vuori, will take over the stage and tell us more about 5G and low latency needs.
Oliko nuola ylös? Okay. Good evening, everybody, or good afternoon, depending on from where you're watching. My name is Rasmus Vuori. I'm the Vice Dean at Aalto University Arts, Design and Architecture, and I have a background in interactive and electronic art, and I'm actually going to talk from a slightly different perspective than the technical perspective. Oh, there we go. Whoops. Sorry. Low latency needs is the topic topic for today, and 5G creates an environment where we can do quite a lot of really interesting things. But first, I might say that for us artists, some of the marketing and the discussion about 5G has really not been the thing that immediately turns us on. The promise is, and we're more interested in what we can do with the medium as a creative instrument. And to explain this perspective, I plan to do a bit of a dive into history, where digital media has started as a creative environment, and how we come to the situation where the really interesting things come in the next generation of digital media. Some of this might be things that you already know from before, so bear with me, but I think these are all part of a sequence of events that are really important to get to where we are right now. When computers were quite new, people, of course, didn't really think of them as media things. They were computational devices. But quite early, there was some creative use of computers as well. People started to make games and communicate with computers and over the networks. And one of these really original games were text-based adventure games like Zork. That was one of the first creative storytelling environments that were done with computers. The next step was to start creating visuals, graphical things, designing pixels. Experiences with pixels, games again, Flight Simulator, maybe one of the first really big computer games that still exists today. Another game, a classic from centuries ago, decades ago, was Leisure Suit Larry's adventure game, a graphical adventure game where you play the antagonist Larry in his adventures in an urban environment. After a while, oh, the clicker is not moving. Okay, next one. Human-computer interaction was the next logical step in the research for computer design. Graphical user interfaces were introduced and made popular with the Apple Macintosh, one of the first computers for regular users who don't have a technical background. An interesting thing when we talk about the topic today is also that speed was a critical design element in the Mac as well. Steve Jobs was very adamant that it has to boot up really quick. We shouldn't be waiting for it. It should be immediately available. So the responsiveness was important already then. Another thing then that came within the development was the increase in data capacity. First, we started to store things on floppy disks. Then we used CD-ROMs. And when CD-ROMs arrived, we thought, oh, they're huge. There's an amount of information that we can store on these disks. Right now, we think of them as really small. But that was a significant step to distribute much more information. Another of the early time hype words were also interaction. The interactivity was a critical element that was envisioned as an important component of the medium. When digital TV was introduced, there was a lot of discussion about media home platforms, MHP as a platform for interactive TV, but it didn't really fly. Something was missing from the equation. It wasn't bidirectional. But what changed from those early days? This was the kind of first generation of digital medium for creative use. A big shift came when the internet became popular, web browsers became popular, and mobile data was introduced. All of a sudden, we had access to the network everywhere, and it was free, and we had or not free as in free as a free beer, but it was available. We had availability to the technology, and we had availability to software, and we had reasonably priced hardware. So we had unrestricted communication, we had a standardized way to distribute visuals, and we had very flexible technology that managed to communicate with each other. This created a new industry with digital distribution of media in a way that wasn't possible before. And some of the views and the promises, for example, on-demand services, all of a sudden became everyday thing. But from those promises, it took about 10 to 15 years for them to become commodities. So the key thing was interconnectivity, the formatting, and the availability of data. The next relevant step came with bidirectional media, the communication. So the feedback from the audience or the users and the people online back into to the network. A classical example of this is Facebook, of course. We participate in Facebook, and we also provide content to the medium itself. Another example are computer games. When we play computer games, we participate in the medium itself. So the participation becomes a key component of the experience. Now, what do we expect to come next? What's the next step in this development? Whoops, I jumped a bit far. The next step is generative content, generative media. Traditionally, we've separated data from code and considered that the code is a static thing and data is a different part. But actually, data is code, content is code, the visual is code as well. And when we start to design for a generative environment, the processing of it becomes also a key component of what we design for this medium. Another thing that I like to point is the difference in terminology in the creative industries. I would like to talk about artifacts and people, not necessarily as content and users. For designers, the artifact, the expression is the key thing. And the audience might be people, they are participants or players, but not necessarily passive users. So we have an audience in mind and their experience. We're designing for their experience. Also, art and design have a slightly different approach to the environment. Art exposes the questions that design attempts to solve. Oops, now it jumped a bit too far again. Sorry about the clicker. Science fiction is actually a really important driver for innovation. And I'd like to take a detour now into the fictional paths as well. This is Chappie, a robot with an existential identity crisis. This is a caricature of science fiction, but it actually opens up some really interesting questions in itself. Another really famous science fiction movie is The Matrix. The whole idea with The Matrix is that we're living in a completely simulated environment, a completely virtual environment. And one of the key components in here is also what we're talking in this fictional science fiction is artificial intelligence. Artificial intelligence still is becoming more and more mainstream today. We also have artificial intelligence in reality. But the artificial intelligence in science fiction is often very dystopian. But is that so far away from the reality as well? To design a proper artificial intelligence, it is actually quite hard to make it really good. And a little anecdote, the dystopian version of an AI can actually happen by accident. And that happened in reality a few years ago when Microsoft introduced the Tay AI on Twitter that was just mimicking and learning things online, and all of a sudden it started to mimic really bad things. It became extremely a bad AI. That was because we had only taught and trained the AI to mimic reality, and we didn't teach it ethics. So the recipe for dystopias if we don't take consideration to ethical perspectives of things. Now, let's see. 5G, oops. Sorry. 5G is the next thing here on our horizon, our event horizon. So what are the interesting things in 5G for the creative professionals? It's not the radio frequencies, not the modulation, not the power usage, chip design, elegant code or compatibility. Of course, those are really important things for engineers and for technical people. But what is interesting for us is the immersive technology and the immersive environments that it makes possible. Every comedian knows that timing is everything. And also for me here, when I've been pressing the clicker, it has created some surprise elements with disrupted timing. It is key of our experiences. But also another thing is that when we have an expectation of something to happen, we do something and the reaction should be immediate. And the anticipation of something to come and the connection in our brain is super important of that thing. And that is a component that so far has been missing for most of the things we do. There's always, it takes a long time for some things to react. And even the smallest differences in timing and latency makes the experience completely different. For example, if we send images to our eyes, if we show a video, and the signal is slightly off sync from one eye to the other, all of a sudden we become really dizzy and we feel like we're drunk. Another thing is that if we hear two sounds that are almost the same in both our ears, when we hear the slight difference in sounds, actually our brain compensates for that and creates the full environment, how we listen to a stereoscopic environment, due to the slight difference in the sync of the time, in the timing of the sounds. So this latency is key for the experience. Now, some of the visions of future use and the criticality of that. This is Bruce McCall's illustration from the New Yorker about a vision of a future road trip. This, of course, is it's a comical version of what the future should be like. But there are some expectations here that are quite real. NASA has experimented also with VR experiences for a long time. This is from 1989. But of course, this required really expensive technology then. But the latency is a key thing for this experience. There are other science fiction versions of visions of the future. Like in Minority Report, the user interface is completely gesture based. To be able to do something like this is of course science fiction, but this is based on topics and concepts that would actually work and have worked in laboratory environments. The latency for something like this becomes really critical for this to actually work. With a delay in interfaces, in gestural interfaces, or in AR experiences, the experience, we have a disconnect from the reality. It's not possible to do this without having immediate reactions to everything that we do. Otherwise, we would be out of sync from reality. So augmented interfaces, they create sensory experiences that are really critical for latency critical. Now again, back to the designer and artist perspective. From the audience perspective, it's critical and interesting to know about the what. Audiences are interested in the what. What are they experiencing? What are they experiencing, and what do they see? But from an artist and a creative perspective, we're interested in the why and how perspectives. How do we do this? And the next generation of creative professionals in the digital field, they design behaviors as experienced designers. So that means that the skill set also has to be different. We're not only designing visuals, not designing user interfaces only, but actually designing experiences. That means that designers need to have a proper understanding of what I call the 5 E's. Let's see. Ethics, emotions, empathy, expression, and aesthetics. So these are the key components for designing or creating artifacts into the digital medium. The technology is, whoops, not the previous one. Go to the previous one. The technology is instrumental. It's key that we have working technology. But for artists and designers, the technology is a tool. It's an instrument to perform in. And the instrument itself is relevant and it's super important. But if we have a concert, we're not going there to listen to the Stradivarius violin. We want to experience the piece. So the performer needs to know what they are playing, and they need to have really good instruments. If you give me a Stradivarius, you don't want to listen to me playing because I don't know how to play with it. But if you give a really good violinist a Stradivarius to play with, he can perform in an excellent way. So these two, the technology works and goes hand in hand with the performance and the artist creations for these mediums. And with 5G technology, the next step that's missing from creating immersive environments, the latency, is the next step that we've managed to solve. That was presentation. Now, if you have any questions, please. Thanks.
like we don't have questions, at least yet.
Feel free to throw me a question on Twitter, Rasmus Vuori, if you have any questions or comments. Sorry about the clicking.
Okay, we have one. How do you see the prospects for VR mass adaptation? Is that going to happen?
VR mass adaptation. I think the augmented part is the more interesting thing and the more relevant thing. Depending on how you think about VR or AR, the fully virtual experience has some potential in some cases, but I think the augmented dimension of having a direct connection to reality in one way or the other is where the biggest potential has. So otherwise either you virtualize yourself into other locations, or you expand the information available where you are at the moment. So I think these are the areas where there are some really interesting or large potential, both for artistic and creative use, but also for practical uses. But of course, for game and fiction, there is it's possible to do things and experience things that are impossible in a virtual environment. And for example, the complete different change of scale and scaling and the sort of spatial experience can be extremely different. But it's kind of interesting that in almost all of the VR experiences, we are so used to experience a world where there is gravity, and there is no gravity in a virtual environment, but still there's an up and down and some kind of a gravitational things that are being designed into that. But what if we can learn or unlearn this perspective of things and truly experience things in a unrestricted spatial environment? Usually, however, the reason why I think it's the AR's perspective is where there's a large potential is also because there's adaptation. Big adaptation requires quite a large amount of familiarity and only a reasonable amount of novelty. And the AR route into the virtual is the way where we have a reasonable amount of familiarity, and the novelty part becomes a reasonable step. So maybe it's a stepping stone into a VR environment as well to make it more mainstream. But I think that's the route it will take in practice. And the reason why I think is because the VR has actually existed for as long as I've been working with digital medium. Already in the 90s, there were quite a lot of VR experimentation going on, and that the distance from the reality to virtual reality is quite high, and that's why I think it's the AR route is the route to go. Also, AR is actually, from another perspective, it's actually something that the virtualization of our reality is actually really old. We haven't done it with technical means, but we have all kinds of symbolic meaning to spaces and emotional attachment to locations as well. And now we're just creating a new representation of that symbolic meaning and using digital tools to create that. So it's actually part of a natural continuum. I hope it wasn't, you need to consider that to be a dismissive thing of VR. I think there's huge potential in VR, but I think it would take longer for it to become mainstream because of the significant or more significant cognitive step that it requires. There will always be experimental things and niche products long before a product becomes really mainstream.
Okay, we have a question. Is the lack of VR AR utilization, is it a problem of devices or applications?
Devices or applications? Well, of course, you have to have the devices there. The hardware has to be there, and it has to be robust and reliable. Otherwise, it doesn't really work. But I think it's actually it's probably going to sneak in the back door in surprising ways where we didn't really expect it. But what is key is that it has to be robust and it has to be fast. And it has to be very responsive and be accurate. Otherwise, we will just turn it off. It has to give us it has to give some value for the experience for it to work. So it has to be something that benefits us and that we don't even pay attention to anymore. It becomes a transparent part of our experience that just supports us. And that way, then it really becomes part of our everyday experience. And then it also becomes a transparent part of something that we expect to be in there. And it definitely requires hardware that makes it that transparent. So we need to have devices that support that. But then also the applications need to be thought through in a way that support that. But I think it's hardware first and then software. And then when we have that kind of applications, then it becomes really transparent, and then we just expect it to be there. I sometimes, when we talk about these expectation, refer to automatic doors. If we would tell somebody 100 years ago that when you go to a supermarket, you just walk in and the doors are automatic, they would have thought that's some kind of magic. But now we have an expectation that there are sensors that adapt, that notice us and open up the doors automatically. And if the store is open, we just walk into the door and we get surprised when it's not opening. So the expectation is that we have some kind of a hardware, we have sensors that detect us and that it adapts to the environment. So a natural thing in here is that the kind of technology that augments our reality are going to be things that with sensors that react quickly enough, give us some additional benefit, some functionality that we start to think is natural, and we just adapt to it and we start to expect that it's there automatic always. And there are all kinds of functions already that does that, and we have automated systems that react when we sit in the car, and it adjusts the car seat and things like that. But those are not augmented reality things, but it's an augmented part of the experience already. But also projections of information around us, giving additional information in new ways that we haven't experienced before. So all kinds of ways there is where the augmentation will sneak into our everyday life. Quite soon, I actually expect to see much more of this kind of experiences, because the hardware is already beginning to become cheap enough for this kind of things. We also have headsets, for example, and devices that have so many sensors in them that we can now detect and know where we're looking and how we're walking and these kind of things. And when we start to figure out what kind of applications we can do, where we can create responsive reactions and responsive things that are immediately connected to the things that what we're doing, then we manage to make successful also applications that are gives us an additional added value to the experience of our everyday life. Any other questions?
Is there any possibility that 5G could start as some kind of a new era of culture and arts?
New era of culture and arts. Yeah, I think it opens up possibilities to do things that haven't been we haven't been able to do before. Definitely, from the perspective of how we experience things, and there's this development has definitely happened in shifts. So we've had clearly generational shifts. So the first generation was when we just had the computational aspect of things, and like I said, that we just figured out that we can actually program things to do things. And the next thing was that when we had the mass distribution, we had the networking effect. What 5G makes it possible is with the low latency, is to create experiences that are connected also not only distributing the information, but the speed of delivery and the immediacy of it makes it possible to generate experiences that haven't been able where the delay has been a problem. And that definitely makes it possible for a shift in the experiences again and what we design for it. But it's kind of difficult to predict what kind of artworks, what kind of things would be there in that environment. Some of the vision, some of the fiction and some of the things that we have envisioned will probably come through, and some will look really silly as well. And maybe in 10 years' time, we will look back at the things that have been envisioned now and think that they're kind of funny the same way as when we look at these postcards from the last century where they were envisioning the future. For example, I think you've probably all seen these pictures with telephones with images and then they're talking into these horns. And something went absolutely right. There was definitely, we can communicate with images and sound right now. That's clearly there. But the design of the handset was really funny. And probably something like this will be in the next step as well. So the actual solutions and what becomes mainstream will probably be quite different to what we expect today. But some of the things will actually happen there. And the experiences will definitely be very, very different to what they are today. The immediacy and the immersion is possible in a completely new way when we get instantaneous speeds, or the time to react is so short that it actually disappears from our consciousness and we don't think about it anymore. As an illustrated example of a similar shift is when first photography was invented. You managed to take a photo, a still image of a situation. And then somebody realized, okay, that you can actually put them in a sequence and create the motion, an effect of motion. And now those pictures were just put in such a fast sequence of images that we don't think about them as still images anymore. We experience them as flow. So the same thing comes now with the sensory data that we can give and experience, how it goes both ways. And when that latency and that speed becomes so short that we don't think about that exchange anymore, it becomes transparent from the medium's perspective. So that was a long answer to a question that probably yes. But to get there, I think it's really key to understand not only the technology, not only understanding how the data is transferred in the network, but also understand the effect it has on the audience and what we're trying to experience. So the design of the full experience, everything from reading the input from the participant to what kind of triggers, what kind of effects we're also sending, to understand this feedback loop and the mechanism and designing for this feedback loop becomes a key component there. That means let's say we can for example create entertainment that adapts to how the audience is reacting. This is one of my kind of favorite topics. And let's say if we're designing, if we're creating a horror movie, if we have some really fast computational system that can first of all react to the audience, then it can adapt to the reactions there, and it can change and start to go bifurcate into ways that pushes things into more scarier environments. If we realize that we show a little bit of a spider and we realize that somebody reacts to that, and then you show a bit more of that. So the computational system can adapt in that direction. Or if we create a comedy, we can instead see that what kind of elements are the ones that are triggering that kind of reactions in the audience, and then we can change into that direction instead and start to make more funny things. What are people laughing about? So this kind of algorithmic design that reacts really quickly becomes possible with a more computationally intensive and low latency medium.
Questions at this point, and sorry, we have one question.
Okay.
As you mentioned Minority Report, one fictional tech popped into my mind, the retina-based marketing, or it's how it's defined. It helped target particular individual. Everyone would see customized visuals on the same screen. How far in the future is this turning into reality? Has this something to do with virtualization?
Well, I have to say I'm not that I don't know exactly that much about that particular technology, but what's clearly is that the personalized experience is not only in the future, it's here already now. And when we carry these devices that we use to experience things, they know quite a lot of us, and the very personalized experience is clearly something that is here to stay as well. And it doesn't have to be connected just to the retina, but we're carrying with us already so much devices that give a lot of information from us. So it is a personalized experience, and when we go to a computer, it gives away who we are. How this is being used is of course a different thing. It's really interesting from marketing perspective. So marketers are using it, but there are also downsides to this, and we also get into a significant privacy debate. What kind of things what's ethical to do here? Because it actually opens the door for quite a lot of manipulation as well. But it's not only in the future. It's definitely here right now that we have these very personalized experiences when we open up. When you go to Facebook, for example, the view you get is always personalized to who you are. When you browse the network, all the ads and everything detect who you are, and they get very personalized. Even if we try to shield ourselves from that perspective. From a creative perspective, it's still missing. It's not that mainstream yet, but I think already Netflix also uses that to personalize, for example, what kind of things it presents and what kind of images it shows is also personalized to your preferences, and some kind of an algorithmic behavior is built into that. And to understand both the parameters that are involved, as well as what kind of things we generate and how to build this kind of mechanisms, I think are key for what you call content creators. It means the artists and designers in these mediums. And I actually think that there's room for artworks that kind of expose these mechanisms as well and teach us how to work with this and play maybe a bit more with it. It could be much more provocative as well. And art has a role not only to explain, but it can also you have a role to provoke things and open up and maybe even teach an audience how to be more critical of the experience, because we know that art is fiction, or we expect it to be fiction, but it still gives an experience and maybe also can be a bit of a wake-up call of how we can be manipulated when we understand that it's an art piece. Traditionally, we consider art to be nice and aesthetically pleasing, but I personally think it's also interesting to see artworks that actually are thought-provoking and open our eyes to options and questions that we might not have been able to think about before. So I think there's a significant role for art in this field as well. And then, of course, when we do design, then we create tools that that help us achieve specific goals, for example. But sometimes entertainment itself is not necessarily achieving any other goal than generating an experience that can be somehow thought-provoking or pleasing or whatever we wish for in the moment.
At the moment we have no further questions, so I'd like to thank you very much for your lecture. There's been some new knowledge to everybody in this course, as the course has been quite technical in some sorts, and it's great to have a look into the field of arts as well. So big thanks for your lecture.
Thank you very much, and thank you for the questions.
will have 4 experienced specialists on stage discussing a topic which has been disregarded under the coronavirus reportage. Next 1.5 hours will be assigned to climate change and its solving with technology. Our next speaker has experience from a wide range of assignments and fields. He has seen what it's like to work for both private and public sectors, as well as the third sector. With experience from Nokia as a head of Research Center Africa and from the Finnish Red Cross, he has now proceeded to Aalto University to develop sustainability solutions. Let me introduce the climate change specialist Jussi Impiö. Welcome, Jussi.
Hello, welcome on behalf of Aalto University. My name is Jussi Impiö. I'm head of sustainability solutions from Aalto, and I'm going to talk to you about 5G and sustainability. My own background with technology goes 20 years behind. I have been working in the interface of developing new technology and technology research and societal challenges around the world. When I started studying roughly 20 years ago, Victor Papanek's Design for the Real World was the first coursebook that I was made to read, and it left a permanent mark on me. And in 2003, I started working with Nokia, and my specific focus was to develop social media or citizen journalism tools for marginalized groups in the world. And that was the first project that took me to African continent. And while I was visiting East Africa for the first time, I came across a town, or more like a village, on a river bend, somewhere on the northwest of Kenya. And that village was empty. And I was there with my local fixer, Moses, and he said that he didn't have an answer why the village was empty. He said that a year ago it was still there, and we managed to find one person from the village, and he said that the village has moved. It's not by the river anymore. It's on the hilltop. And we were quite amazed because it's rather arid area, and it would make perfect sense for a village to be located by the river. But when we started to ask for the reasons why the village had moved, we were even more amazed when we learned that the village moved to the hilltop because it had mobile phone connection. And that was the moment when my perspective to technology and society changed permanently. For thousands of years, it had made sense to set up human settlements by streams. You get water, you get fish, you get transportation, and you get also protection. And now, because of mobile connectivity, this village had preferred all those basic elements, has preferred mobile connection to all those basic elements. And based on that finding, I understood that technology will have a permanent impact on low-income countries, and it's up to us whether that impact is positive or whether it comes with the downside. So after taking this insight and lots of research insights back to Nokia headquarters, I got a mandate to establish a research center in Nairobi. And in 2007, I started Nokia Research Center Nairobi, and I led the research activities of Nokia in the African continent and Middle East. And our focus was to understand how communication technology can enable societal development, socio-economical development in the context of developing world. So in this picture, you see how some of the work days were outside the office. Some of the work days were like this. We traveled in rather difficult environments to reach different kind of groups of people. Here you see a village meeting and nearby Lake Victoria, where we just introduced the world's cheapest e-reader device for our pilot users. So we made 1,000 units of e-readers with more than 5 million pages of preloaded content, and the price of the e-reader was a bit more than $10. It was super simple, super basic device that you could connect to an ordinary mobile phone via the audio cable, and you could order new books and newspapers through the audio, like when you back in the days you accidentally called into a fax machine and you heard those noises. That's how you updated the new content. Then we worked with a lot with local self-help groups, local groups that were self-organized, and our focus was really to understand not really to find the problems and not kind of like focus on the challenges and the problems, but find the resources and abilities that these communities have, what they have used for decades, maybe even for longer periods of time, to feed themselves, to flourish, to keep their culture alive, and keep new generations educated. So building the new solutions, digital solutions, top of the existing strengths of the community is something that we found out that is essential as an approach. When I say we, I mean our research team, which was around 50 researchers all across Africa, and our networks of satellite studios in 3 other African countries. And with this introduction, I want to bring you to the today's theme. And the main question for us today on the table is where in the systemic picture is the core sustainability value of 5G? So the massive sustainability challenge that we are facing currently in the world is simplified and illustrated here on your left. So basically, well-being, economical growth, and use of natural resources are all strictly tied together. And sustainability of the planetary resources is on dramatical decline. And while well-being, economical growth, and use of natural resources grows, sustainability dives deep. And the solution, what we need to do is very simple. We need to disconnect the use of natural resources from well-being, economic and economical growth. So why isn't it done yet? This is how the world of any goods, any consumer goods looks today. This is simplified map of sourcing and manufacturing a mobile phone. It starts from the mines in 15 different countries, goes through the finery and smelting processes in 8 countries, and through different kind of steps of logistics and manufacturing, it eventually ends up to our shops and then ends up to user, and the user has a role in either storing the old and unused or broken device or recycling it. This kind of like illustrates the complexity that we have built around our economy. And 5G is one of the kind of like promises or carries one of the promises of digitalization. So providing more efficiency in the system. So making systems to be more efficient. Too often the efficiency just means that we end up making the same shit that we have been doing, but we make more of it, we make it faster, and we make it cheaper. So we actually end up increasing the gap between the economical growth and sustainability. So what we would need to do is to aim at having closed loops with the materials. Instead of going through each time through the virgin raw materials, we should go to 100% closed loops with the materials. And aim up energy saving on each of the steps. So basically making less stuff but better, repairing and updating stuff that we own and use, and sharing of resources. Like cars sit on the parking lot 97% of the time. If you buy an electrical drill from a store, the average life cycle, average usage time during the life cycle of electrical battery operated drill is 11 minutes in its entire lifetime. So there are lots of opportunities for sharing resources in our environment. And if we look through kind of like a 5G lens, there's a massive opportunity for enabling these kind of like sustainable goals and needs for repairing, updating, and sharing of the resources and improving the cyclicity of the equipment and the raw materials. Then on top of the sort of like in a way obvious natural resource-based sustainability topics, 5G touches also very critical equality, human and social equality topic, which is the digital divide between continents like Europe and Africa, countries within the continents, and urban environments and rural environments, and different kind of income groups. And now I would like to walk you through some of the suggestions for you, how you could kind of like look into challenges of developing world and specifically Africa through the opportunities of that 5G provides. So I'm not going to provide you with any solutions, but I'm going to provide you headlines of some key challenges that 5G might have an impact in actually solving these real world challenges. The first and the most important bottleneck for bridging the digital divide is still the price of data. In average African country, Kenya in this case, data is 12 times more expensive than in India. It's 2 times higher than in Finland, when average income in Finland is 27 times higher than in Kenya. So if you multiply your monthly phone bill by 54, you get the idea of the enormous price that data has for average user. And the top 5 data prices in country are all in sub-Saharan Africa. And this is still today the major hurdle for people accessing, having access to internet services. And for example, most of the stuff that I'm going to walk you through next are dependent on this. If this is not going to be solved, not many of the issues that I'm going to walk you through will ever reach the significant number of population in African countries. Okay, urban mobility. Commuters in Lagos, a capital of Nigeria, they spend 30 hours in average per week in traffic. So it's almost another work week in the car, in the traffic. The wasted time and energy and money that gets into the commuting is just mind-blowing. And unless you have experienced that yourself, you cannot fully appreciate the kind of like stress and the sort of like a decrease in quality of everyday life when you spend 30 hours in a week in Lagos traffic. In bit smaller city in Nairobi, it takes 45 minutes to get to a meeting in the Nairobi city area, one way. So it means that basically you can have 2 meetings per day. So quite a lot of sort of like potentially easy solutions for 5G technology available in this space. Now to area where the complexity and sort of like the systemic challenges increase quite dramatically. The economical growth and the population growth in African countries are the highest in the world right now. And it's massively important that the economical growth is based on renewable energy. Otherwise, all the achievements in more industrialized countries done in cutting CO2 emissions will be overrun by the economical growth in Africa. And we need the economical growth in Africa to increase stability because climate change will bring lots of challenges in food production, food security, and other social challenges that follow these kind of like fundamental functions of society. So we need energy systems which are zero carbon. We need energy systems which are distributed. Africa is 10 times the size of India. The distances are long. We have broadly distributed settlements, villages, towns, cities here and there, with people with very low average income. So, by economical terms, building massive electricity infrastructure it does not get justified very easily. So, all kind of lightweight distributed systems are needed. Again, 5G might have also solutions for this, but it's also these energy systems will provide the enablers for 5G and communications altogether. Power is needed to run everything. And then affordable prices. So this kind of like a challenge requires business models, technical solutions, applications, and new type of business models. Then the area that I already touched is food production. We have massive challenges on fragmented farmland and very low efficiency in food production. And 50% of the food gets wasted on the way from the field to the market. And there are lots of improvement needs there, and also needs for improving the food production, making more kind of like processed foods and accessing international markets with African foods. Then there are two basic opportunities which are massive in learning: access to high quality education, specifically professional education for basic jobs. Then healthcare, accessing high quality diagnostics, accessing quality treatment and distribution of medicine. So, quite fast running through rather complex and rather big societal challenges, where part of the solutions could be within the reach of 5G and its applications. So now I encourage you all to think, where in the systemic picture is the core sustainability value of 5G? So that we do not end up sort of like lubricating the system, which is harmful, but we actually end up leapfrogging and making new systems which actually provide more sustainable ways of living. Now it's up to you to go and find it. Thank you.
Thank you, Jussi, for your interesting presentation. During the world's leading startup event Slush in December, it's usually around +1 Celsius and pitch dark in Helsinki. Slush is especially known for the amazing number of volunteers who organize the event and run the whole community of Slush. However, today it is a beautiful summer day in Helsinki, so what could be better than having the CEO of Slush, Miika Huntunen, on stage discussing how to create progress. Welcome, Miika.
All right. First of all, thank you for the invitation. My name is Miika. I'm the CEO at Slush. And Slush is, when we started as an event, we gather annually thousands of startups and investors under one roof and aim to ensure that startups meet who and what they need. These days, we're doing a lot of other things as well, especially in online. And due to the pandemic, we have been slightly on hold for the event, obviously. But for the other things, we have been doing plenty of other stuff. Slush mission is to create and help founders to change the world. And change the world is pretty connected to an idea of progress, although change and progress are not necessarily the same thing. But I'm going to talk about today about how to create progress. So the presentation and the set is structured to 3 parts. So first I'm going to make a case why we are maybe making less progress than we used to compared to maybe 50 years back. Secondly, I'm going to walk you through a few examples why this is the case by comparing some historical, let's say, infrastructure project to something that we have done today. And finally, I'm partially answering to the question how we actually going to create the progress. But although I have to already at this point say that nobody knows 100% what exactly creates that, but why we should be more interested about this is the key point what I'm making. So let's start. So let's start with the picture. So in your mind, draw a graph of life expectancy in the developed world between 1900s and 2020. Does it look linear? Does it look exponential? Or does it look more close to some kind of logarithmic or converging to up or down? So this is the case. This is United States, and we of course all know that United States has its own particularities in the healthcare system, but it's a fairly good indicator of the life expectancy in the developed world. And as you can see, it's definitely not exponential. It's not even linear after, let's say, 1960s. And it's actually, in the end, converging to some kind of maximum value. And I think the first takeaway from here is that life expectancy is not necessarily the really good first order measure what human progress is, but it's definitely a good second order measure of all of our efforts of creating the progress. And it's good to know that the rate of progress we humans, as humans make is not some kind of constant to some kind of infinite value. But I think what we can see from here is that we're not clearly making as much progress than we used to do in the life expectancy. So basically, as we can see, for the past couple of years, it has started to converge to some kind of like maximum value there. What is interesting, however, is that when we compare this to the healthcare spending, we can pretty clearly see that we are spending more money, but at the same time making less progress. So this is the percent of the GDP as a spending, and obviously it's a relative measure. And it has gone up from around 4% to 18% in the US. And of course, this is once again US based, and we have to keep in mind the particularities of the US healthcare system. But basically, not only we're creating less progress, we are investing 3.5 times more. And basically the rate of progress is decreasing. And I think this is pretty worrying. And this is the reason why I wanted to talk about this today. And just give you some ideas and inspiration over the course of this time you are thinking about different topics. So let's move on. This is another graph. Labor productivity as a relative metric once again as a 5-year moving average. And basically, of course, there are different ways to present this, but the trend line is similar in all research. And basically, for example, in the EU, we have gone down in 60 or 70 years from 5% to close to 0. Once again, we are getting less bang for the buck as we're doing things. And clearly, we are not changing the world as quickly as we used to. And whatever the absolute rate of how fast we create progress or not is, I think we can summarize it to how quickly we can get ourselves out of this mess that we have created. So for example, when we're tackling with climate change, pandemics, you name it, progress is a measure of whether we can actually deal with this thing in 100 years, 50 years, 5 years, or in 1 year. And I think there are two hypotheses why this is the case, why we are creating less progress than we used to in maybe 50s and 60s or 70s. And before the examples, I'm gonna briefly think about them. So I think the reason and why this is actually possible might be due to that it's intrinsic or it's institutional. You can argue that the reason that progress is getting slower is intrinsic. So it gets intrinsically harder to move the world forward the longer we go. So we need more researchers, more science to create those breakthrough discoveries. We need more money, more scientists, once again, to cure the next disease, capping the human life expectancy. But there is also reason to believe that this is somewhat institutional problem. So, and what that means is that we have set ourselves to be either much slower or much more resource requiring in order to create the same amount of progress that we did. Now I'm going to show you a couple examples why I believe this is in a way very much institutional problem than intrinsic problem. And these examples are actually from entrepreneur and CEO co-founder called Patrick Collision, founder of Stripe. And Patrick has his own website where he collects projects that have been executed in the history exceptionally fast. And I'm going to walk you through a couple examples and compare them to recent day. So let's start with the Empire State Building. Obviously, by then, the tallest building in the world. Empire State Building was completed in 410 days, at the cost of $564 million US dollars in 2019 value. And when we compare that to the One World Trade Center, completed in 3,112 days at the cost of 3.9 billion US dollars in 2019 money. So basically 8x longer, and it took basically 7x cost more to build this. And it shouldn't be anything more difficult to build skyscrapers these days. Maybe they're a bit more fancier, but what's the case here? I honestly don't know. Second example, New York subway. Once again, not maybe the subway that we are traveling these days, but 28 stations completed in 4.7 years. And when we compare it to this year, this time, this is the Second Avenue subway, which was completed in 70 years for 3 stations. So what? 10th of the stations in 4 times longer time horizon. So definitely Länsimetro is not the only subway project that took this long, but once again, this change or the comparison is pretty significant. Moving on. This is maybe a bit cherry-picked project. This is the Alaska Highway that was completed in 1942 and 1943. And practically 1,700 miles completed in less than a year, at the cost of slightly less than $800 per meter in 2019 value once again. And once again, a slightly cherry-picked comparison to these days, but this is something that Patrick Collision also uses on his website. Vannes bus lane from 2001 to 2021. 2 miles projected to be completed in 7,003 days at the cost of $100,000 US dollars per meter. So what, like 1,000 times more expensive, taking much more longer. Doesn't make sense. A couple more examples. So I am personally so young that I don't remember a time when you can practically pass over the Atlantic from London to New York or New York to London in less than 3 hours. So this is obviously Concorde in 1996, which was later ended as a project. And if we compare that to these days, so 25 years later, the time we can go over the Atlantic is slightly less than 5 hours in the best conditions. So this is Boeing 747 from New York to London in 2020. So if we go back, 25 years later, it takes 2 hours longer to go from London to New York. Once again, it doesn't make sense. It shouldn't be intrinsically harder to make that traveling time and traveling speed faster. It has to be somehow institutional problem. And last example is about the Apollo missions. And obviously when Yuri Gagarin flew to space, America decided that they are not going to lose the space race, and they did not. In 1969, they went to the moon with Apollo mission, and practically what the thinking after going to the moon could be is that then we're gonna go to the next body outside the world, outside the Earth, I'm sorry. So, for example, Mars. And even today, we are not even remotely close of getting to the Mars. And you can argue that space travel is whether it's needed or not, but it's definitely something that increases the human consciousness and understanding of the human race itself. So after all these years, we are not even remote close going to the next body or planet beyond the Earth. So now moving to the part that what should we do about it? And obviously I don't have the ready-made answers. There is way too little research on how we create progress and how to fund science that maximizes the amount of progress we do. But there are a few data points that we have covered at Slush, as we get plenty of data out of startups that we can then analyze. So let's walk them through pretty quickly. But before that, I want to highlight that the world is changing faster and faster, but we are not necessarily making more progress as it is. But this is just as a context. If you think about the market caps, this is once again US focused, but if we think about it, what has happened is basically a complete flip, and there is no overlap. So basically what started as retail companies or similar has switched to like having 5 most valuable companies being a technology companies. At the same time, the time of how long it takes to build these companies has decreased significantly. When it was in 1995, roughly 100 years, now it's between 16 and 45 years. And this is also a reason why at Slush we are so driven by entrepreneurship and why we think it's one of the best ways to change the world, because you can practically build a company, the most valuable company in the world, making something valuable in 15 years. So a couple lessons that we have identified through data at Slush. So the first one is that we analyzed the funding raised and the performance by applicant gender. So whether the money was raised by female founders or male founders and how they are performing. And what we noticed is that although female founders are raising less money, they're actually making more revenue per funding raised. And also more revenue per employee count. And yet, in Europe, we have a systematic problem of that 92% of all European venture funding goes to the all-male teams. And this, in my opinion, both from the equity side, but also from the general ability, what kind of problems we solve, because you can only solve problems that you can see. And it's clearly also, if the team is diverse, performing better, it doesn't make sense why we're still here. This is something we should change in order to create progress in the future. Second thing, we compared about the average revenue by founding year in hardware versus software companies. And we noticed that we are not thinking long enough. So basically, for the first 4 years of company existence, software companies outperform hardware because, well, software is pretty scalable. You don't necessarily need that much investment upfront. But after 5 years, hardware starts to perform. But still, once again, if you look on the right-hand side, a vast majority of VC funds operate in this 10-year cycle. So they are, the existence of the venture fund is 10 years, which is often too short for these breakthrough hardware companies. And at the same time, European deep tech seed funding looks like this, so basically converging down. Clearly not enough activity there. We are not thinking long enough. And also, one lesson that we noticed over our data in relation to creating progress is that we're betting to companies that are already out there, or to the ideas that are already out there. If you look total funding into European startups, it has totally exploded in the past years. We are about to make a record year out of 2021, despite the pandemic. But at the same time, the total pre-seed funding in Europe is actually decreasing. So practically the risk capital is going to companies that already exist and not maybe maximizing the total amount of ideas who get invested. And this is the last example of our data. So practically in 1980s, 12x more funding went to researchers under 40 than researchers over 50. And this is once again what we're betting what's already out there. In 2017, 5x more funding to the researchers over 50 to researchers under 40. And if you think about the median age when Nobel Prize winners in physics did their work, it was 34.5 years old. So maybe it's an example of when institutions age, they maybe get more risk averse, but it's still a problematic point that we have found. The point I'm making is that there is a reason to think that we are not making as much as progress than we did. We don't know what exactly is what we should do, but it's something that you and I should be more obsessed about, how to actually solve this thing, because in the end it's affecting all of us. And the thought I want to leave you with is what the Finnish youth or the youth in general is doing in the next decade. And this is maybe a bit controversial, as I've written it, that the smartest Finnish youth, of course there are many different career paths and options what you can do. But this is more maybe what I have seen through Slush, is that maybe in the early 2010, and before that, people went to work in companies like McKinsey or consultant companies, Kone or Nokia, these large corporations. And then onwards from 2010, smart individuals, young people start to think about going to the startups. So Supercell, Volt, Swappy, Rovio, Small Giant Games, Smartly, and this has been the past decade. And my question is, what will be the next decade? What will be this decade where the most ambitious people around the world want to be? And I hope, and I actually believe, that these will be in companies that are, of course, both growing incredibly fast, but also creating a positive impact to the surrounding society. And I will finish up with a quote: "Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has." Thank you very much.
Thank you, Miika, for a genuinely thought-provoking presentation. Finns and Swedes have a long history of competing against each other in every sport there is. But when it comes to the development and utilization of 5G technology, we strive to make it better together and apply it in as many applications as possible. We are pleased to present our next speaker from Sweden. Mangnus Frodigh has over 26-year-long career history from Ericsson, currently serving as a vice president and head of Ericsson research.
Thank you for inviting me to Aalto University Summer School. My name is Mangnus Frodigh. I'm head of Ericsson Research, and I'm happy to address you all here from the Ericsson studio in Kista, Stockholm. The title of the talk today is on the 5G and 6G and how that could be an enabler for a green acceleration. I think we all know that we have a significant challenge ahead of us. We really need to find things that could get us going. And it's important then to try to start with the technologies and the fields where we are ready to apply technology already today. This slide shows how we need to reduce our CO2 emissions. And in order to meet the targets, we will have an important target to halve the emissions by 2030. And of course, the earlier we can get started, then we have more time to reach the halving by 2030. And the more we wait, the more urgent it will be, of course. So this coming 10 years will be extremely important. And this is really the decade where the 5G will be rolled out. And so we will have a gradually more and more sort of connected possibility, enabling technology, and that could drive this exponential change that we need to make sure that we get going forward. And in order to analyze this, we have been working very actively on this exponential roadmap 2030. This is a report that was first presented in San Francisco 2018 and an updated version in New York Summit 2019. So look a little bit more into the details of that report. We can here look at the different sectors. And in the report there is 36 specific solutions outlined how we can then work with the different sectors in order to reduce the carbon emissions and reach this 50% cut by 2030. And looking a little bit more specific then to the 5G, 6G and the sort of the ICT sector, that sector is also, of course, contributing to the carbon footprint. And that is around 1.4%. I will return to that and the importance of keeping that, of course, under control and even lower that. The more important thing is, of course, that by using the ICT technologies, we can contribute to the reduction in all the other sectors. And we estimate in this report that that reduction could correspond to like a 15% reduction. And that's a significant contribution to the 50%. So I think we have a lot of things to contribute here by using the ICT technologies. If you, for example, think about the different sectors here, and if you think then on a smart agriculture case, of course, if you are able to have a lot of sensors, so you get a lot of exact data about the field and the crops, then you can have much more precise actions in the farming, of course. And by that efficiency gain, you are then able to reduce the carbon emissions from that sector and increase sort of the efficiency. And this goes for all different sectors here. And I have one example that I would like to share with you. And this is in the transportation sector. And here, of course, we all understand that you should go then from diesel-driven trucks to electrified trucks. And here we have done this trial together with the startup Einride that is sort of behind the truck here. And we have done that together with Telia, so it's been Ericsson and Telia and Einride looking at this use case. And the main saving is, of course, to go to the electrification. But when you do that, the cars, the trucks tend to be a little bit smaller. They also need to stop and charge. And then you realize that, yes, you save a lot on the fuel costs, but you get additional costs on the driver's side. So in order to make this going, you need also to think about how you can make these autonomous vehicles. Because then you get a very, very nice combination of electrification, autonomous drive, and that is facilitated by then the connectivity of these vehicles. So we can support this kind of transformation at scale. So by the connectivity, the automation, and then the electrification, we are achieving a huge saving here in this example. Returning to the ICT sector, and we have been following this carefully for 25 years, and we are really seeing how the global carbon footprint of the ICT industry has been developed here according to the green curve. And it has been fairly stable, right? And we all know that the amount of data that is used in this network have been increasing exponentially. And we have not only sort of the connectivity, we have also the data centers and everything. And then there is a lot of misconceptions here that believing that the ICT footprint or the footprint of the ICT sector really is proportional or correlated with the data traffic. And then if you make these assumptions, then you can sort of calculate that the ICT sector will increase a lot, right? But that's not a fact. It's so that now in the pandemic, we had a traffic increase of 25% in Sweden, for example. And the power consumption of the ICT network only increased by 1 or 2%. So there is no strong correlation between these two. And looking at the curves here, when we go forward, we even estimate that even though we will have an enormous increase of the data through the systems, we should be able to actually reduce the footprint from the ICT sector. And then it's also so that the energy that is used is to a very large extent being sort of renewable energy. And the ICT sector is one of the largest purchasers of renewable energy. So looking here at the radio networks and the communication networks then that we are sort of closest related to here at Ericsson, we can see the different generations here. We can see the 2G networks, the 3G networks, the 4G networks. And the energy consumption here has been sort of going up because we have added one system on top of the other, and it has been difficult to turn off older systems, older equipment. And the data has also been exponentially increasing. So will it be the same now introducing 5G? Would that be yet another thing on top? No, it will not, because 5G has been designed in order to be much, much more energy efficient than previous generations. You can say that the energy consumption was one of the key design criteria for doing 5G. And how it works here with 5G is that it doesn't really consume so much energy when it's just turned on and waiting for traffic, so to say. Then it can go down in sleep mode And when there is a traffic, it goes up and takes the traffic, and then it can go back down in the sleep mode again. And by this, the power consumption will not go up in the same way when we introduce 5G. Then, of course, it's important to modernize the network, to really have new modern equipment. So you can take these advantages that we are now introducing with 5G and move the traffic over to 5G and get all of these advantages. And by that, saving on the old technologies. And as the terminal fleet evolves and more users will have 5G capable phones, you will be able to move traffic onto the 5G, and by that sort of keeping the power consumption down, although that you are carrying so much more data. On top of that, we also have quite a lot of energy saving software that can be used on top of that. And it's important then to build the network and the capacity according to what you need in order to break the energy curve here. And we have looked at the countrywide example here. So we have looked at the power consumption of a network for a complete country. And then we have simulated how we are building out this network, taking more and more traffic. And we are seeing here that yes, it is possible to break the energy curve. So this looks really, really good. Finally, I would like also to take a discussion here on the 6G. And 6G is still in research, so we are still looking for sort of the understanding exactly the use cases, understanding exactly how the network will be constructed, etc. But we see very, very interesting developments here. And it's very much the communication between these two worlds. So we have the physical world where we live and we have all the machinery and the environments. And then we have the digital world. And we are seeing now how all different industries are creating digital twins of their products. And we see how a digital representation of our surroundings is being created by different actors. So we will have this physical world that will be equipped with an enormous amount of sensors collecting a lot of data about the physical world. This data will be then transmitted over to the digital world, where we will have a real-time updated digital version of the physical world. In that digital representation, all the products will have its digital twin. And the digital twin will be able to start to interact, and you will be able to learn what from the past, what sort of have happened in a similar situation, and you will understand what will happen going forward. So we will be able to have this learning from the past and predicting the future. And by that, you will also then be able to take actions. And then you will sort of calculate action that you would like to see. You will transmit that action back to the physical world where you have actuators. It will be the robots, the self-driving cars, etc. that is being connected. And by doing that, you can be able to then control the physical world. So by that, you will have this digital representation and programmability of the physical world. And when you look at this in between the physical and the digital world, you see that there is a lot of connectivity going on here. We will have the intelligent machines communicating with each other in order to solve complex tasks. We will have us humans being in the physical world, but we would like to have all of these augmented experiences. So we will move from the physical and be present sort of in the virtual and in the augmented worlds. So we have the Internet of Senses. And we have this digitalization and programmability then between these two representations. And I would claim that by doing this, we can continue on this journey and develop technology also for the next decade that can be used to continue to reduce our CO2 emissions and still offer a lot of growth, because a lot of the values that are being created going forward will be created in this digital world, and that will sort of require sort of no material, etc. So there is a lot to be gained by optimizing this future. And I think this is really where we are at the 6G research now. We are talking about how this future could look like. And we are looking for technologies to be able to provide the needed functionality. And the energy consumption of the ICT sector will continue to be one of the key targets, obviously, in order to go forward here. Thank you very much. And the question is really how technology then can be used to curb climate change. Thank you very much.
Thank you, Magnus, for your interesting keynote. Our next speaker has a long and successful career. He has served in various positions in the United Nations from 2006 to 2018. As well, he has served as Director of Disarmament, Arms Control and Non-Proliferation at the Ministry in Helsinki with remarkable results. Let me introduce Jarmo Sareva, Ambassador of Innovation, Ministry of Foreign Affairs of Finland. Welcome, Jarmo.
View on innovation and digital development. Thirdly, I will say a couple of things about innovative finance for sustainable development. And then finally, I will conclude on a topic that I find extremely important and inspiring, and that is gender and tech and gender and innovation. Now, to begin with innovation, what do I see by innovation? I would see it as a significant positive change. It is a result. It is an outcome, but it is not a gadget. Because seeing innovation in purely tech terms kind of bastardizes it. So innovations can be service-related, they can be design innovations, business innovations, and social innovations. And let me also note that innovations can be, and very often are, of the frugal kind. This means that there are many innovation opportunities in the South-South context, or even in the South to North direction. Advanced industrial societies can actually learn from frugal innovators in developing countries. And even if Finland is geographically in the far north, we not that long ago were innovating ourselves frugally and socially. And our advancement from one of the poorer European countries about 100 years ago to where we are now, one of the most advanced countries in the world, was due to a combination of technological and social innovation. And I would also note that in Finland, social innovation has been particularly prominent in the health and welfare field. And I always mention the Finnish maternity package, the äitiyspakkaus, which has been successfully spread to many other countries as a prime example of Finnish social innovations. Another example is the free school meals since the late 1940s, when we were still far from wealthy and were recovering from the war, but were able to institute hot free school meals, which not even all our Nordic neighbors currently provide to school children. And what is important, what is kind of exemplary with regard to the free school meals, they are continuously improved with student input. And this is an example of design thinking, the need to design our innovations with the users. I would also stress that any innovations, especially those of the social kind, are time and context specific. One innovation can mean one thing in one country and something completely different in another. Somebody's innovation is not innovative at all in another country. So the political and cultural context is important to understand and to take into account. Now, and this is of course important for you, the audience. Innovation is also about a willingness to experiment and to risk failure. And here, Finland and Finns have become much better. We're no longer averse to failure. And this brings me to the promise and power of startups. And it also underscores the need for startup and early stage funding. But like startups, civil society organizations, NGOs, have been the source of many social innovations. And this brings me to my final point about innovation. It's about collaboration between the public and private sectors based on a quadruple helix model, collaboration between the government, the academia, the private sector, and civil society. And this is a particular strength of Finland, the ability to collaborate across the aisle, across sectors of society. My second theme is innovation and digital development. Finland ranks consistently near the top in both digitalization and innovativeness of its economy and society. And as I already pointed out, innovation, both tech and social innovation, has helped make Finland into what we are today, a prosperous and open society with social justice and equality for all. Now, based on our own experience and our own values, which are thoroughly Nordic and European values, we have also made a long-term commitment to digital cooperation and innovation at the global level. We see innovation and the beneficial use of digitalization as indispensable for sustainable development and reaching the 2030 Sustainable Development Goals. They must serve, and this is really, really important, innovations and tech in general must serve human agency. They must be human rights based, and they must aim to strengthen the rules-based international system. So human agency, human rights, and the rules-based international system. Finland is committed to forwarding innovation and digital development as part of our development policy and the SDG agenda. And in this regard, we are a strong advocate of digital inclusion. And I'll return to this issue later when I discuss the agency of women and girls being a central priority for us. Now, we also strongly acknowledge the role that innovation and inclusive digitalization can play in building back better and strengthening the resilience of systems such as health. We have seen over these past 14, 15 months that resilience is really key in building back better and greener. We work bilaterally, regionally, and in multi-stakeholder partnerships to advance inclusive digital transformation in developing economies. And we do this by engaging the Finnish private sector and other innovation system actors in this work. And of course, we partner with the UN. I will not go into the detail, but we have been systematically building a small niche presence for the UN here in the Helsinki metro area, focusing on innovation and impact investing. So this brings me to my third theme, which is innovative finance for sustainable development. Just to remind, more than 5 years ago now, the so-called Addis Ababa Action Agenda, negotiated in the context of the UN, called upon the mobilization of resources to fill the financing gap to meet the sustainable development goals of 2030. Back in 2015, it was estimated, and now the gap may be actually higher. It was estimated that the gap is in the magnitude of roughly $2.5 trillion annually. And it's been long ago recognized that a gap of this magnitude will not and cannot be filled with public sector contributions alone. Instead, both public and private financing are needed. But this means that financing needs significant scaling up if we are to honor the pledges given to 2030. Because right now we only have 9 years to go, and the pandemic has set us backwards in many of the goals, not the least in Africa. So blended finance can be a great tool to increase the amount of resources available to developing countries. I would note that Finland was actually the first European country to establish a 114 million euro blended finance vehicle for clean tech back in 2017. And we are continuing on this path, and we do encourage other countries to do the same. And in line with our European commitments, we recently submitted for evaluation a National Recovery and Resilience Plan, as all European countries were expected to do. And with this instrument, green recovery in Finland is supported by 50% of the allocated public resources, which amount to approximately 1 billion euro. And then these are met and scaled up with another 300% private sector financing. And the EU, I'm telling this because the EU's Green Recovery and Resilience Facility is a good example of SDG climate action due to, firstly, strict overarching conditions or taxonomy related to climate mitigation and adaptation that any chosen activity, including industry, has to meet. So the EU's taxonomy is an important enabler to scale up sustainable investment. It was already referred to in a previous intervention that another area which does require major public and private sector contributions, is mobility. We heard about the long commutes in places like Nairobi. And as part of more sustainable cities and communities, mobility as a service is becoming an increasingly important part of the solution scope, in addition to more traditional infrastructure investment. For climate smart and sustainable cities, decarbonized mobility can be achieved through investing in both electric public and electric private mobility. Such an alliance model has been used in Finland, for example, in the city of Tampere. And further investments in services and infrastructure, such as charging stations, call for both public and private contributions. So what does this scaling up then mean for these investments? It means continued patient efforts to match public contributions with private sector ones and beyond. And this requires measures which are sometimes beyond our own comfort zone. We must allocate resources with pretty strict strings to meet the SDGs and the green goals. So combining financial instruments with taxonomy helps us reach the goals. And as we know, regulation can both level the playing field for industries, for companies, but it can also foster innovation. And California, the fuel economy standards first set by the state of California have been have given a great boost for innovation in the automotive sector in the US. Now, my last and my fourth and last theme is gender and tech, and this is the one that I already said I'm pretty passionate about and inspired about, because gender equality is a key priority in Finland's foreign policy. Much has been accomplished, but much more remains to be done. And as we already heard earlier this evening, the inequalities in tech are issues that absolutely must be stressed. As Miika noted, 92% of funding goes to all male founding teams. So we need to address the inequalities in tech, in which manifest themselves in so many ways. I haven't maybe stressed enough that digitalization and new technologies, including 5G, by the way, can pose both great possibilities and threats and risks. This applies also in the area of gender equality. And digitalization has been said to be the next great divider. And therefore, before these divides gel up, it is crucial to find solutions now, fast, before the digital divides, including the gender one, become ever deeper and much more difficult to address. And the pandemic has highlighted the urgency of the issue. Finland is currently one of the co-leads of the so-called Generation Equality process, a 5-year flagship project to take the gender equality agenda to the next level, and also to try and roll back the efforts of those who themselves are trying to roll back gender equality. And we are a co-leader of the Technology and Innovation for Gender Equality coalition or action coalition of this 5-year campaign. And what do we want to do during the next 5 years, together with the other leaders and those who want to commit, others who want to commit to using technology and innovation for gender equality? First of all, we want to bridge the gender gap in digital access and competences. Secondly, we want to invest in feminist or gender transformative technology and innovation. Thirdly, we want to build inclusive, transformative, and accountable innovation ecosystems. And finally, and this has been Finland's priority in preparing the program, the blueprint of our action coalition. Our priority has been to prevent and eliminate online and tech-facilitated gender-based violence and discrimination. Now, technology and innovation are relatively new issues on the international gender equality agenda. And therefore, the challenge for us has been to create a framework for international cooperation at this crucial intersection of tech, innovation, and gender equality. Now, even in a country like Finland, the technology sector is still pretty segregated. The workforce is surprisingly gender segregated, but fortunately, we are taking many actions to try and move forward to make technology more gender transformative, more inclusive, and to bring fully the 1/2 of Finns and the future, fully the 1/2 of humanity into tech as equal players. And here, the role of the private sector, as well as men and boys, is crucial. We need men as role models, men from the tech sector as role models in changing the culture in the tech sector, because the key challenge in this all is how often young women who enter the tech sector end up leaving after a couple of years. And this is due to kind of a pervasive male bro culture that we need to change from within. So with these words, I thank you. I went through 4 key themes for Finland, which are kind of innovation, defining innovation in broad terms, including social innovation. Secondly, providing a Finnish view on innovation and digital development, our partnerships to help developing countries use digitalization for good and for economic development based on human agency. My third point was about innovative finance for sustainable development, fully realizing that the traditional means of public financing will absolutely not be sufficient. And fourthly, I presented the Finnish view on how important it is to make tech more gender sensitive, more gender transformative, and more inclusive. Thank you very much.
Thank you, Jarmo Sareva, for your amazing keynote. Now we have a possibility to ask some questions from the professionals, so please send your questions via chat function on YouTube. Looking forward to tomorrow, the topics include, for instance, how technology can improve productivity in developed and developing countries, how 5G affects the demand for ICTs, and 6G and Internet of Skills. Thank you for all of our amazing speakers and participants for today. We'll see you tomorrow.
Yes, thank you very much. We're back from the studio here in Aalto University. We received so many questions from you guys. We're so happy about that. I would like to ask, we have Vice President from Ericsson, Mangnus Frodigh here, and then the Ambassador of Finland on Innovation, Jarmo Sareva, here to answer our questions. So first, I'd like to ask you the question, do you cooperate with startups and citizens organizations in developing nations, especially in the field of 5G and networks?
Yes, I think we have been this triple helix type of setups. They are more typically in more developed countries actually, with the private sector, university, and the community, the public, and the state in governance into that. When it comes to more developing countries, we have been more like providing the connectivity and applications and being part of creating this sort of new economy that have been established based on the mobile connectivity then in different developing countries. So we haven't, to my knowledge, been that active in these kind of more research projects when it comes to the developing countries.
If I may,
yes, please.
From the Finnish government side, our development cooperation, the projects that we have bilaterally or regionally in developing countries, focusing today mostly in Africa. From the outset, we have been stressing the importance of engaging the private sector in these countries to foster private sector development, and startups can be and are an important partner. But to be very frank, the startup culture in developing countries has emerged only pretty recently, but it is emerging rapidly. Before the pandemic, I traveled, twice to Nairobi and once to Nigeria in a fairly short time, and I was really struck by the energy, the sophistication, and the skills of the startup entrepreneurs that I met in both countries. I was also struck by the fact that many startup companies have been founded by individuals who had been trained, who had lived in the West, but who had decided to come back home because they saw genuine business opportunities in their home countries. So this is absolutely an area where we will and where we must focus increasingly in the future in our bilateral development cooperation activities. We have been kind of focusing more in recent years on so-called multilateral development cooperation, that is cooperation with and through the UN system. But even here, the UN, increasingly at the country level, is focusing on private sector cooperation, including with startups. So long story short, the answer is yes. And of course, civil society is truly important because they often have the kind of civil society, both locally and their partners from Finland. They have a good, in German, Fingerspitzengefühl, a very good sense of the prospects, the opportunities at home, and they can also ensure that the development cooperation projects are human-centric and strengthen human agency, human rights, and an open society. Thank you.
Yes, thank you very much for your answer. I'd like to ask Mr. Frodigh a question about basically why not? Why is there's no too big of an activity yet? Is it more of a developmental issue, or is it a financing issue, or is it you don't have customers there, for example? Do you have some prospects on that?
Yeah, but I think perhaps it's a little bit the explanation here that Jarmo was talking about, that the potential sort of startup partners have been a little bit limited, and of course there's a lot of innovation happening on top of the connectivity and the networks. But then of course we have our customers then, and we are trying to help our customers to have like garages or places where they can interact with possible startups, etc. But to my knowledge, I mean, I haven't been in all of our different markets, right? But to my knowledge, it's been more in the Western side that we have momentum around this, and a little bit less when it comes to the development countries. Yes, I think that's still the fact. But if this now is changing, I think we will be very glad to try to onboard these new startups. I think we have the possibilities. We are in all countries, and we are working closely with our customers, and they are also, the customers are also now looking for these opportunities. So I'm optimistic.
Yes, thank you very much. That's great to hear that there's a...
Let me make one important point in this regard.
Yes, please.
And it's about what standards will developing countries, especially Africa, build their digital future. Will those standards, which then determine the normatives, quite often determine the normative side of their digital and technological future, will they be based on a human-centric, I would call it European model, or on a more authoritarian, centralized, government-centric model from China? And then what will be the role of the US and the US tech giants? This also bears ultimately to the future transatlantic technological relationship. Will Europe and the US be able to act together as, and this sounds old-fashioned, but as the free world against the more authoritarian models coming primarily from China? And this is a very, very difficult question, not only to European governments, but also to European companies such as Ericsson or Nokia here in Finland, for that matter.
Oh, thank you very much for that. A bit more detailed question about 5G. So we know the topic of this session is about climate change and this kind of sustainability and all of its abilities. So a question about 5G. What could be those kind of applications where 5G and the new network technologies, new technologies could decrease emissions and pollution? For example, energy creation. That's been a really a topic that has been rising in the West, at least at this point. Is there any?
Yeah, I think there are a lot of good examples. If you were to talk about the energy sector, I think all the solar and wind and everything, that this will be this very distributed, and you will have issues with the synchronization and the robustness of the system, and then the connectivity and the possibility to have real-time control of different things will help in order to create a smart network, the smart energy network that everybody talks about, right? So I think it has a key role to play in order to again, like a facilitator for the other technology areas to advance. So I think that's a typical example how it come into play. And then I had this electric truck where it also sort of facilitated that change from diesel to electrification, right, by sort of helping with the automation of the drive. So I think you can see that, and then there are some trivial examples that if you have everything connected, you can do all the different things you want to do in a city a little bit more efficient all the time, and by that you can save emissions. And then I think as soon as you look at something and you connect everything, then you have this sort of 15% just making it more efficient. But of course, we also want to change. The real effect comes when you do something completely different, and then you can get this 90% saving. Right? So it could come in different ways, but it's important to start, because to get the first 10-15% will be very, very valuable, right? To get started.
Yes, definitely. Thank you very much. And next question is that we know that 5G will play a crucial role in establishing, for example, smart buildings, smart cities. But what could be these 5G-powered applications that actually bring value to human value to life, to actually create that user-centric design into how to ensure that, to create kind of solutions that people actually need?
Yeah, I don't know if you actually need it, but there's a lot of things, right, that where you can think of having a much more immersive experience. It could be sports, gaming, entertainment, where you will get much more involved in that experience compared to the screen that you are looking at today, right? And that could possibly activate you more, and you can be part of the game or something, and we can perhaps get away a little bit from this sitting and watching screens all the time, right? Which is not good for us. So that could be a real benefit, I think, if you were to look at this the consumer side. But then, of course, 5G is very much now opening up a lot of things, and it starts a little bit more on the enterprise side, I think. Then when that's established there, perhaps more and more of this robotification and gets closer to consumers again, but that could be a little bit in the end of this 10 years time frame. And then we might have a lot of robots around us that could help us with a lot of different things, which will be very nice, most likely, right? But I think we need to go through a phase a little bit through the enterprises first.
I would add that I think mobility, 5G, but not only decarbonizing mobility, but also making mobility easier, faster, more enjoyable, can be a great boon to human satisfaction and quality of life, especially in developing countries. Miika, we heard from Miika some very startling statistics about the time that people end up wasting in the gridlock traffic in the great urban megalopolises of the developing world. But there are great opportunities also in learning, improving educational opportunities and health. So it will open many avenues for improving human lives across the entire gamut of human experience.
And there of course 5G is, but there is more important that 4G as well is being built out on the already existing GSM to 2G sites, right? There is some sort of basic coverage, but it's not, the data coverage is not built out, and there I don't think there is any technical issues more or less. There is product solutions which are very optimized for these things, but still it isn't the most attractive investments for the telecom operator. So it gets further down on their investment list, right? They have other more attractive investments that they do first. So I think to get the investments and building out sort of the mobile broadband and then really maximize that coverage, that will really give all these benefits that you talk about. 5G then will make it that even faster or something like that, but to really get it out here, the mobility services to everybody and then have devices, the phones that is a little bit more low cost, of course, in combination with that would really be required, and the values are enormous. Yes.
Okay, it's so great to hear your thoughts on this. Let's the session is already a bit over time, and I know it's evening, so I wish to let you go continue your evening. But with the last questions, when we are connecting the previously unconnected, what will be the biggest kind of result, a consequence of that? Do you have any thoughts on that with new technologies, for example?
If I may start, I think it's really, we're at a fork in the road here, because we have two futures to choose from. As a result of the technological opportunities that we have at our disposal, be they 5G, be they AI, quantum computing, or others. We can either choose a pathway which strengthens human agency and human rights, strengthens open societies, takes us back from the polarization that has become all too pervasive in the digital spaces, and strengthens ultimately democratic societies and systems. But this requires choices to be made, with not all of which are easy to make. And in making this choice, we have to bear in mind that there are genuinely bad guys out there, be they criminal organizations, be they unscrupulous businesses not playing by the rules, or be they governments which are intent on using such technologies to advance authoritarian, undemocratic purposes and goals. So we have choices to be made, and this requires patience. It requires cooperation from democratic countries, and it also requires choices from us all at the personal level. Do we want to be part of the echo chambers that kind of foster a culture of disinformation and fake news, or do we want to foster a culture which is based on critical thinking, media literacy, and the ability to engage in a fact-based dialogue at the societal level? Thanks.
Thank you very much. Do you have some
I have nothing to add on that. I think you said it very well there. But of course, connected, unconnected, it also have obviously all these basic values that we have seen connecting sort of the first billions set of people here, right? And how that have advanced the growth and democratized a lot of different things for people that have been able to be connected. So all of that is of course still valid. Then now we are seeing how we are entering this. Yeah, it's a very, very powerful technology we have, and it could be used for good or for bad. So I agree, we need to work hard to get it to mostly be good, right?
Yes, definitely. Thank you very much for this session. It's been such a joy to have you both here. I think we'll be back tomorrow with new sessions, for example, with technology for social, ecological and economical development top session tomorrow. So I would both like to invite you both there if you have some time in the afternoon and in the evening. But as for today's session, I'd be happy to close this on these thoughts. It's been so great to have you both here. Thank you very much.
Thank you very much.
Thank you.